Okay, so yeah, so like I said, my plan is to just kind of go quiz by quiz, do a couple slides, and then we can go over the quiz questions. And then again, if you have any questions that come up, anything you want me to expand upon, any topics you want me to talk about more, then I can do that. My iPad's about to die. I will just use those quizzes. That works fine for me. Okay, so you guys are all good and can see everything. Then we can go ahead and get started. So just to start off, one of the kind of main goals of this class was to give you guys a little bit of understanding about our place in the universe, like where we are in the scale of things, both in space and in time. We live on the Earth, and the Earth orbits the sun with the other planets in our solar system, and then our solar system is in the Milky Way galaxy. The Milky Way galaxy is part of the local group of galaxies. That local group of galaxies is part of the Virgo supercluster of galaxies, which is part of that large-scale structure of galaxies that we saw, that kind of big web, they call it the cosmic web of all these interlaced filaments and nodes. So we, on Earth, we're just this teensy, tiny little piece of the universe, but we're also the only place that we know of that has life. So that's pretty important. That's pretty cool. And this is where we live our entire lives. And so, so many people ask me stuff. They're like, oh, you study astronomy. Does that make, all your problems feel really small? And I don't think it does, because it's all kind of to scale for me. Like, if my problems feel small, then my joys feel small. And I don't want that to be. Like, we are small in the scale of the universe, but what happens in our lives is still important to us. And I think that's something that we can be humbled by astronomy, but like, don't forget that you're important too. So we're part of that Virgo supercluster. There's like 10 million superclusters in the observable universe. When I say the observable universe, that is, we can only see as far out as light has had time to reach us from since the beginning of the universe. So the universe was created, 13.7 billion years ago. We can only see 13.7 billion light years away from us, because light from farther than that hasn't had time to make it to us. So our observable universe is this sphere of 13.7 billion light years in every direction around us. There's 350 billion Milky Way-sized galaxies in the observable universe. There's 7.5 trillion just galaxies in that universe. There's 30 billion trillion stars. We've been around for just a teensy fraction of the history of the Earth. And then the Earth has existed for like less than a third of the history of the universe. And so we are very kind of new on the universal landscape. And one really, really important thing, one of kind of the very, very fundamental things to understand about astronomy is this concept of look-back time. Light takes time to reach us. So the sun is 8 light minutes away. It takes 8 minutes for the light from the sun to reach us. So when we look up at the sun and we see it, we're seeing it how it was 8 minutes ago when that light was emitted. So when we look at a galaxy that's a light year away, we see that galaxy as it was 1 year ago. When we see something that's 100 light years away, we see how it was 100 years ago. So the farther away that we look, the farther back in time that we are seeing it. If it's 1 million light years away, we're seeing it as it was 1 million years ago. So this allows us to look back in the history of the universe by looking at things that are farther away. So starting with the Earth, our Earth, it rotates on its axis once every 24 hours. So that's the line that goes from the North Pole to the South Pole, and it rotates around that every 24 hours. So that's what causes day and night, because half the time you have one side facing the sun, and then you've got it turning around that. And when the other side is facing the sun, it's night on the other side. We also orbit around the sun once a year and a quarter day, which is why we have leap years. because it takes 365.25 days to go around the sun. So we have to make every 4 years, those 0.25s add up to 1 year. Or add up to 1 day. We got to tack on an extra day. The rotation of the Earth is tilted compared to the way that we go around the sun. So this causes the seasons. So, like here, if the sun is in the middle, on this side, it is winter in the northern hemisphere. If someone is standing here in the northern hemisphere, they're going to go around like this. And they're going to spend more time in darkness than they are in light. So they're going to have a longer night and a shorter day. If someone is down here in the southern hemisphere, they're going around the Earth like this. They are going to have a longer time in day and a shorter time in night. So they get more sunlight. The sunlight is also at a more direct angle, so that makes things hotter, so you get seasons. When it's on the other side, it's the opposite. You have a longer day in the northern hemisphere and a shorter night. So the turning of the Earth around its axis causes day and night. It's why we have a daytime and a nighttime. How much of that 24 hours is broken up into daytime and nighttime is because of this tilt. If the Earth were not tilted, if it were just straight up and down, then it would always be 12 hours of daylight and 12 hours of nighttime. But because of this tilt, we get this change with longer days and shorter nights to longer nights and shorter days. Okay? Sorry, I don't have a laser pointer to make things easier. So the moon, just like the Earth goes around the sun, the moon goes around the Earth. And it takes 28 days to go all the way around the Earth. And the moon also rotates on its own axis, but it takes 28 days for the moon to do one turn on its axis. So because of this, the same side of the moon always faces the Earth. And I'm going to kind of draw this off. It's kind of weird to think about, but if we have the Earth and we have the moon here, right? And there's like a mountain on the moon or whatever, and it's right here. And the moon goes around the Earth. If I look at this 28-day cycle, and the same mountain is always facing Earth, then this mountain has done a full revolution as you go around, right? It was facing the bottom, now it's facing the side, now it's up that way, and it goes back to facing down as it goes around. It's all the turns. Does that make sense? Okay. So, the Earth goes around the sun, the moon goes around the Earth, and there's a tilt between their two planes. Let's see if I have a little cardboard. I'm going to take it out. And one of them. So, you've got the Earth going around the sun's here in the Earth, and then the moon going around the Earth, and they're tilted like this. So the reason we don't have eclipses every month where the moon passes between the Earth and the sun, or on the other side of the Earth, if they were like this, every month we would have an eclipse. We would have the moon going around this edge, come between the Earth and the sun. But because it's like this, it's only when they're in a configuration like this that the moon passes between the Earth and the sun, or on the other side of the Earth. If they're like this, then the moon is never going to hit that line between the Earth and the sun. So because of this tilt, given this little picture here, we only have eclipses some months. So kind of the biggest part of this section that you guys are probably not as familiar with is light. If I say light, if I say electromagnetic radiation, if I say photons, those all kind of refer to the same thing, right? So I know it can be confusing if we're going back and forth on terminology. Electromagnetic radiation is like the official like physics term. Light is kind of our more colloquial term, and photons are like the particle of light. They're the tiniest little piece of light that travels. So when we are seeing light from, this ceiling lamp, I don't know. Light, it's sending out a ton of photons. So my eyes are receiving photon after photon after photon from this. All light travels at the same speed. That speed of light, you guys are familiar with that term, so just know, like, it doesn't matter what type of light it is, because there's different types of light. It doesn't matter what type it is, it's all going to travel at the speed of light. So we break up light into this electromagnetic spectrum, from radio waves to gamma rays. The visible light is just that opt in this picture is it's for optical or visible. That's the visible light is, and that's just a little piece of this full electromagnetic spectrum. So there's photons of all different types coming at us. Our eyes are only tuned to pick up a certain type of photon, but the other ones are all around us. We just don't see them. So what differentiates these types of photons? Like, why are these types different? There's kind of two interrelated things. One is the wavelength. This is the distance from peak to peak of the light, because it goes in a wave. So this to here, this distance is the wavelength. So you see this light over here has a long wavelength. All the way on the other end at those gamma rays, it has a short wavelength. From peak to peak, there's just a little short space. Frequency is this idea, if you were standing still and the wave was passing you by, and you said, okay, in 1 minute, I'm going to count how many peaks go past me. Or really in 1 second, how many peaks go past me. That's your frequency. Its units are per second. Right? It's peaks per second. Wavelength is distance per peak. Frequency is peaks per second. So if you have a shorter wavelength, you're going to have a higher frequency, right? If these peaks are closer together and the light's traveling at the same speed no matter what, then if you're standing still, more of them are going to go past you in the same amount of time. And if you have a longer wavelength, you have a lower frequency. Higher frequency is a higher energy light or higher energy photon. Lower frequency is lower energy. So on this, these radio waves, these are the lowest energy type of light. Gamma rays down at the other end, those are the highest energy type of light. Okay? So if you multiply that wavelength times the frequency, you get the speed of light. So if you are trying to remember, if I go down in wavelength, does that mean I go down in frequency, or do I go up in frequency? You can remember that. Is there an eraser in there? The wavelength times the frequency is always equal to c, the speed of light. So this number has to stay the same no matter what. So that means if your wavelength goes up, your frequency has to go down to balance out, right? To make it equal to the same number. So, visible light, like I said, is just that little tiny bit of the full electromagnetic spectrum, just those specific wavelengths that our eyes pick up and our brain interprets. When you have all the wavelengths of visible light, when you have a bunch of photons that are at all those different wavelengths coming at you, our brain interprets that as white light. And an object, we see an object as the color of the light that it reflects at us. So light hits this, hits my iPad, and the parts of it that are green absorb every color but green, and it reflects green back at me. But a light can only be reflected if it was shined on the object in the first place. So there's white light shining on it, so every color of light is being shined on it, so green can be reflected. But if you are not shining that color, then there's nothing to be reflected, and you will not see any light. So, we did this example in class a bunch. If you have a yellow banana slug and you shine blue light on it, it can't reflect yellow light back at you because there's no yellow light coming in. It's going to absorb the blue light, it's going to reflect no light, and we will just see it as black. Right? So if you shine yellow light on it, it's going to absorb no light and reflect all the light back at you. You shine white light, it's going to take that yellow and reflect it back at you and absorb everything else. So the sun shines down white light at us in all the different colors. Our atmosphere scatters blue light, so it takes those blue photons that the sun is putting at us and it scatters them around. So when we look anywhere but at the sun, we see blue because those photons have been taken away from that sunbeam and pushed everywhere around. And when we look at the sunbeam, it has a little bit less blue light because those photons went and got scattered. The more atmosphere that you go through, the more blue light is taken away from that sunlight. So at sunset, the light goes through more atmosphere than it does at noon. So if we're standing here at noon, and here's the Earth and here's our atmosphere, the sunlight has to pass through this much atmosphere to get to us. At sunset, it has to pass through all of that atmosphere. And the more atmosphere that it passes through, the more blue light gets taken away from that sunlight and scattered away. So when something looks less blue, it becomes more red. Because we have this spectrum, right? Our rainbow, red, orange, yellow, green, blue. Let's just forget about the indigo and violet. If something gets farther away from blue, it gets closer to red. If red light gets taken away from something, it looks more blue. So this blue light gets taken away and scattered away, and it looks more red at sunset when it goes through more atmosphere. Also at sunset, this atmosphere acts like a prism. It takes that light and it spreads it out. So instead of seeing just one sun, we see a red sun. This light gets scattered. We see a yellow sun and then a green sun. And they set one after another. And that's that green flash that you can see sometimes at sunset. It's the atmosphere spreading out the sun into 3 different images, acting like a prism. So, when we're talking about hot things, I kind of told you in the past to separate them into hot gases and everything else. Everything else is generally like solids or plasmas. But you can still kind of think hot gases and everything else. So in that everything else category, if something is hot, it's going to emit light in what is called a continuous spectrum. So that means that or a Planck curve or a black body spectrum. So this specific shape that I'm showing you here is called the Planck spectrum or the black body spectrum. A continuous spectrum is just any spectrum that emits light in all wavelengths. So this spectrum has brightness on one axis and wavelength on the other. So it says that it is putting out more light at a specific wavelength than at other wavelengths. It's putting out light at all wavelengths, but some of them have more light than others. If the spectrum was putting out the same amount at all wavelengths, it would still be a continuous spectrum, but it wouldn't be this Planck spectrum, this black body curve. So there's 3 curves on there, and each of those is for something at a different temperature. So that top curve is the hottest temperature. The middle one is the middle temperature, and the bottom curve is the lowest temperature. As things go down in temperature, your total curve gets shorter, so you emit less light in every wavelength. Yep?
So could we think about the microwave background as...
Yes, the microwave background is a block curve. Yes.
Okay.
Mm-hmm.
Where the peak is at 3,000.
Well, so the whole curve is at 3,000. The peak is at a wavelength. Right, so each curve, the whole curve is at the same temperature. It's just giving off different amounts of light in different wavelengths. So we can imagine this cosmic microwave background as a solid, or it's a plasma, but we can think of it as a solid, and it's all at 3,000 Kelvin, and it's giving off light in every wavelength, but it's giving off the most light in, I think it's not originally microwaves.
No.
It's,
Whatever 3,000 Kelvin is.
yeah, whatever the 3,000 Kelvin light is. And then as that light comes to us and gets stretched, it starts looking like the other ones. So, like I said, as your temperature gets lower, you emit less light in every wavelength, right? So for that bottom curve, everywhere on that line is below the top curve and below that middle curve. But the other feature is your peak wavelength, the wavelength that you're giving off the most amount of light, gets longer. So that hottest top curve, its peak, it's giving off the most amount of light in the blue spectrum. So it looks blue, right? Because if it's giving off light in all colors, and then it's giving off some extra blue light, then it kind of looks like white plus blue, which is blue, right? That middle one, it's giving off, its peak wavelength is in the yellow. So it's giving off light in all colors, but it's giving off the most light in yellow. So it looks yellow. That last one, its peak wavelength is in the red, so it looks red. So as we look at our little rainbow, stuff on this side is going to be cooler. If something looks red, or it's going to look cooler than something that looks bluer. Like, and you guys have seen this, in fire. That middle part of the fire, that hottest part, it looks blue. Like if you're looking at a candle flame. And as you go out, it looks yellow, and then orange, and then red on the outside. Or if you start to heat metal up, first it glows like red hot, and then it gets even hotter up to like the yellow, kind of whitish hot. So higher temperature, shorter peak wavelength, but more light in all wavelengths. Right, so shorter wavelength, higher energy, right? Shorter wavelength, higher frequency, higher energy, and a higher temperature. Things that are hotter have more energy. So that is for everything that's not a hot gas. Hot gases act different. They don't emit their own light just on their own. They don't create light. But if you shine light on them, each little atom or molecule of that gas can absorb certain wavelengths of light. And then later on, will re-emit that light, kind of in any direction. So, in this kind of bottom picture, I have that thing that looks kind of like an egg is like a star or a light source. So that's giving off light. So if we look directly at it, we see a continuous spectrum. We see light in every color. So that's this bottom thing here, right? If we look directly at it, we see light in every color. Then this blob here, that's our hot gas. So as this light travels through the hot gas, some of it gets absorbed. So if we look at this light thing through the hot gas, we're going to see what's called an absorption line spectrum. So this is this continuous spectrum minus the wavelengths of light that got absorbed by that gas, right? Those photons got absorbed by the gas, so we see everything but those. And then the gas takes those photons and sends them back out in every direction. So if you look at this gas, anywhere but directly at that light source. So if you have a star and then a cloud of gas, if you're looking at that anywhere at that cloud of gas except directly at that star, you're going to see this. Those are those specific wavelengths of light that got emitted or got absorbed and are now being re-emitted. It's called an emission line spectrum. So this continuous spectrum is in all colors. This emission line spectrum is only in those very specific wavelengths that got absorbed and re-emitted by the gas. And every different type of gas, all the gas made of all the different elements, is going to absorb and re-emit different wavelengths. So if this is this emission pattern from a specific type of gas, a gas made of something else is going to absorb and re-emit different wavelengths. So it's going to have a different pattern of these lines. And the reason that each of them has a different type of light or different wavelength of light that it absorbs is based on what are called their electron orbital energy levels. You have the electrons in the atom orbiting the nucleus, and each one of them can jump up to a higher energy level. So if you have an electron down here at their lowest energy, they can jump up to a higher energy level if they have just the right amount of energy that they get from a photon. But that photon has to have the exact amount of energy that it takes to make this jump. So this electron here can only absorb the wavelength of light that it takes to make this jump, or this jump, or this jump, or this jump, right? So that's why there's a couple lines on there, because it can absorb a couple different wavelengths. So it can absorb that amount and jump up here. And then it can absorb, another amount and jump up here. And then later on, it's going to fall back down to the bottom and spit back out that amount of energy that it absorbed in the form of a photon. So the height of these steps is different for every different element. So this would be one type of element, and then this is maybe another one. So this one would have to absorb a different amount of energy, a different wavelength of photon to jump up. So it's these different electron orbital energy levels that cause the different emission line patterns for different gases. The solar system, we've got our sun. It is a G star. 99.86% of the whole solar system mass is in the sun. Everything else is kind of just dwarfed by the sun. We have 4 rocky or terrestrial planets. They're Mercury, Venus, Earth, and Mars. These have like solid surfaces and a small atmosphere compared to their total size. Mercury has pretty much no atmosphere. We have our gas giants, Jupiter and Saturn. What he refers to as ice giants, Uranus and Neptune. And then we have a bunch of moons. There's asteroids. There's a big asteroid belt like between Mars and Jupiter, but then there's other asteroids. Kuiper Belt asteroids. The Kuiper Belt is a big kind of asteroid belt outside of the orbit of Neptune. Pluto is a Kuiper Belt object, right? Got demoted from being a planet because we found out that there's a bunch of other things that are kind of the size of Pluto, some smaller, some even bigger, that are out at that same place, and Pluto couldn't clear its orbit out. So it was either make Pluto not a planet, or we have a bunch of extra planets now. So I remember when I first was like, Pluto got demoted, oh, it's so sad, but it really does make sense. Like, you can't just say, you have to have definitions for what is and isn't a planet. And the line was either Pluto doesn't fit the definition anymore, or we widen the definition, and that means that, Quaoar and maybe even like Ceres and stuff become planets as well. And then we have more than 9. So that's why we have 8 planets. There's also comets, dwarf planets. That's what Pluto got changed to. And if you want to be in our solar system, you have to orbit the sun. That's like the big thing of like what defines our solar system, and is all the stuff orbiting our sun. And then the picture on the side is a somewhat to scale image of the distances and sizes of everything. So you can see the sun is by far the largest thing in our solar system. Our little rocky terrestrial planets, Earth, Venus, Mars, and Mercury, those are all really close up. This guy right here, it's hard to see. That's Jupiter, Saturn, Uranus, and Neptune. So all of this all right here, that's Mercury, Venus, Earth, and Mars. They're all really, really close in. And then there's a big distance jump to Jupiter, and then another big jump to Saturn, and then a big jump out to Uranus, and then an even bigger jump out to Neptune. Right, so and things get much more spread out as you get farther away. Like Jupiter is about 5 times as far away from the sun as the Earth is. Some kind of interesting facts about the solar system. So one thing that was kind of a clue as to, they used to think that the Earth was in the center and everything orbited the Earth. And one of the clues that this wasn't quite right was that Mars appears to move backwards in the sky sometimes, right? So if everything is orbiting the Earth, then they're always going to be moving in the same direction in the sky, right? If I'm looking from the Earth to this, it's always going to be moving across the sky. But Mars moves backwards in our sky. And this was called retrograde motion. And they came up with this idea of like epicycles for why this worked. And it's nonsense. But, they thought that Mars's motion, really went like this with the Earth in the center. And then the next time around, it went. So you have this really very silly pattern. And so this was a clue that we've got this wrong. The Earth is not in the center. But if the Earth and Mars are both going around the sun, all of a sudden it makes sense. Because Earth is on the inside, it takes Earth a shorter time to go around the sun than it takes Mars. So the Earth, I like to think of it kind of laps Mars. Like Mars is in front of it, moving in one direction. It kind of catches up, and then Mars is like moving behind it. And then as it goes around the turn, all of a sudden Mars is moving in front. So that's kind of this picture. If you look from Earth to Mars, against the background stars, Mars appears to make this loop. Right? Because the Earth is moving faster. When you're right here, when you're going from here to here, Mars appears to be moving this way. But when you're going here to here, all of a sudden Mars moves backwards in your view. And then it starts to move forwards again. That's retrograde motion. Another interesting thing, so Mercury is the closest planet to the sun. Venus is the next. You would think Mercury would be the hottest, but it's not. Venus is. And that's because Mercury has no atmosphere. It basically got all burned away. Venus has a really, really thick atmosphere. And the greenhouse effect traps all the heat that Venus gets. So on Mercury, the sun's light hits it, and it heats up, and then it radiates that heat back out into space. On Venus, the sun's light hits it, it heats up, and that light can't radiate back out into space because it gets trapped by the atmosphere. So Venus gets super hot because of the greenhouse effect. And then hydrogen and helium are by far the most common elements in the universe. Hydrogen is like 75% of what makes up the universe. But there's very little hydrogen or helium like in the atmosphere of Earth or Mars or Venus or Mercury. And the reason is because at those temperatures close to the sun, hydrogen and helium are very light. They're moving fast at these high temperatures, and they're moving fast enough that they can escape the gravity of the Earth or Mars or Venus or Mercury and escape out into space. So they're moving too fast to stay on the planet and be held to the planet.
I thought the most common element was like dark energy.
I mean, as far as like normal matter.
Oh.
So yeah, so like dark energy has the biggest part of the energy budget. Dark matter is the biggest part of like the matter. And then when you're just looking at like normal matter, 75% of that is helium or hydrogen. And then it's pretty close to 25% being helium. And then just a little bit is left for everything else. Okay. Yeah.
Set of slides.
Yeah, so that's it for the first quiz.
Wait, yeah, you're gonna post this.
Yeah, I can post these. That's fine.
Cool.
Yeah, that's no problem. So okay, my iPad died, so I'm just gonna grab one of these quizzes, and we can go over the first quiz. Is that what you guys want to do? Does that sound good? Okay. So the first problem on this one talks about scientific notation. You guys feel comfortable enough with that, or do you want me to actually go over that one? Okay. So for scientific notation, you want to transform some number with a bunch of zeros in front or behind it into something that just has one number and then a decimal point and then something times 10 to the something. And so the first one is 1,000. And when you move the decimal point, you count how many spaces you moved in. So I want to transform this into something that just has one number in front of the decimal point. So I'm going to move this decimal point 1, 2, 3 spaces. Then I take my new number, 1, I can do 1.0 or 1, times 10 to the number of spaces that I moved. So I've got 1 times 10 to the 3. So I moved 3 spaces. I moved 3 spaces to the left. If you move the decimal point in the other direction, you may get a negative. So The next one is 0.0002. So 0.0002. I need to move this decimal point, so there's just one number in front of the decimal point. I'm going to move it 1, 2, 3, 4 spaces. So I have 2 times 10 to the, since I moved it to the right, -4. If you have a number that is a big number, something bigger than 1, that you're turning into scientific notation, it's going to be a positive exponent. If you have something that is smaller than 1, then it's going to be negative. So this part here, this is called the coefficient. This part is called the exponent. So then there is 1/10. 1/10 is equal to 0.1. So I'm going to move my decimal point 1 spot. 1 times 10 to the -1. That's not important. And then 300,000. I'm going to move my decimal point 1, 2, 3, 4, 5 spots. 3 times 10 to the 5th. Right? Okay. What color is a yellow banana slug illuminated with white light? Yellow. So white light means all the colors. So yellow light comes in with that white light, gets reflected back at us. I think one of the other versions of this quiz asks, or maybe not, maybe they all.
With green light.
Okay, so it did ask, okay, so there was a version asked. Yeah, illuminated, what color is a yellow banana slug illuminated with green light?
Black.
So that would be black, right? If green light's hitting it, there's no yellow light that's able to be reflected back at us. So we just see no light, which is black. So for a solid at, let's do this one. For a solid at 2,900 Kelvin, at what wavelength is the peak of the Planck radiation curve? So this thing here that I showed you, the equation to find out what wavelength that peak is, what wavelength it is giving out the most light in, is your temperature is equal to 0.29 over your peak wavelength. And this has to be in Kelvin, and then this has to be in centimeters. So this says, this wants to know what wavelength. So for this equation, I have temperature. I could plug in wavelength and get a temperature out, but I want to be able to plug in a temperature and get a wavelength out. So in order to do that, I got to rearrange this. I'm going to take it. I'm going to multiply both sides by lambda peak. So this symbol lambda, this means wavelength. These are going to cross out.
Could you have also just divided by 0.29?
So if you divide by 0.29, then you get T over 0.29 is equal to 1 over your lambda peak.
Okay.
So then you could invert both sides
Okay.
and you get the right way. That's one way of doing this, but I think this way is a little bit, you don't have to do the inversion, which can be confusing. Right? So you want your, whatever you're looking for to be on the side all by itself on top. Right? So if I've got lambda peak times temperature is equal to 0.29. Divide both sides by temperature. and I get that my peak wavelength is equal to 0.29 over the temperature. So now I can plug in 0.29 over 2900 at 0.29. So if I turn both of these into scientific notation, this is, I'm moving it over 1, so this becomes 2.9 times 10 to the negative 1 divided by 1, 2, 3, 2.9 times 10 to the 3. If you multiply something in scientific notation, you are going to multiply the coefficients and add the exponents. So if I have 3 times 10 to the 5th times 2 times 10 to the 4th, I'm going to multiply my coefficients, and that's going to give me 6 times 10 to the add my exponents, which is 9. If you are dividing, you divide your coefficients and subtract your exponents. So for this one, this is going to be 2.9 divided by 2.9 times 10 to the negative 1 minus 3. So that's going to give me 1 times 10 to the negative 4. And my units on this need to be centimeters. So on this problem, we give you full credit if you got to this point. If you just plugged in this and put centimeters, you got full credit. Okay? Day and night on Earth are due to, what causes day and night on Earth?
The spin.
It is the spin of the Earth on its axis. The fact that it happens at all. Suppose you lived on a planet with an atmosphere that scattered red light more efficiently than blue light. Label the following true or false for that planet. So the sun would appear bluer at noon than it did at sunlight. So let's think, or at sunset. So let's think about this. So on our planet, it scatters. So you can do this in two ways. You can go back to the basic principles, or you can compare it to ours. On our Earth, the atmosphere scatters blue light, and at sunset, the sun looks more red. So on a planet that scatters red light, the sun should look more blue at sunset, right? We're just flipping red and blue. So that should be false. The sun would appear bluer at sunset than it does at noon. If we think about it just from the basic principles, if I've got light in every color coming down, and the atmosphere takes this red light and it scatters it away, then I've got just green and blue. So it's going to look more blue. The more atmosphere it goes through, the less red light's going to come out and not be scattered. So the more blue it will look. At sunset, it goes through more atmosphere, more red light's getting taken away. It's going to look less red and more blue. And then the color of the sky looking away from the sun during the day would be white. If the atmosphere scatters red light, what color is the sky looking away from the sun during the day? Right, it's going to be red. When we're looking at this, so if we look directly at the sun, we see all the light that comes from the sun minus what gets scattered. If we look anywhere else, we only see this red light that got scattered. Right? This blue light and green light is coming straight through. The red light gets sent all through the atmosphere and then down to us. So if we look anywhere over here, the only light we're going to see is red. What time does the full moon rise? Oh, so So this diagram is, you can draw out kind of this type of diagram to figure out what time the moon rises and sets. So the idea behind this is you draw your sun. I'm not going to draw this because I'm going to kind of go over this quickly. You draw your sun, you draw your earth, and you say, okay, what are my times? If I'm standing here on the earth, the sun is directly above me, it's noon. If I'm standing here on the earth, the sun is right on the other side of me, it's midnight. If I'm standing right here, and I look to the side, I'm going to see the sun, and as time passes, the sun is going to be more above me. So this is sunrise. At sunset, you look to the side, and you're going into the nighttime. So that's sunset. You draw your moons. You don't have to draw this many. You can draw with just the one if you like. And then you say, okay, so, for this, the sun lights up the half of the moon that's facing it. And then you think about what would it look like if I were standing on Earth. So if I'm right here on Earth, looking up at a moon that's right here, the sunlight is only hitting the side that's facing away from me. So there's no sunlight on the side of the moon that I see, so it just looks black. So that's the new moon. For this one, if I'm standing here looking up at this moon, the sunlight is hitting everywhere on the side that's facing me. That's a full moon. On this one, the sunlight is hitting up just half of the moon that's facing me. The other half is not getting any sunlight. These are your quarter moons. It's half the sun, but it's a quarter moon. I know it's weird. And then your crescents. So then you say, okay, where, if I just ignore everything but the one that I want to look at, where do I have to stand so it's rising? So where I look to the side and it's there and it's getting higher above me. So at sunset, you look to the side and see the full moon, and as time goes on, you're getting more underneath it as the night passes. So it rises at sunset. But I'm going to tell you a little trick. If you get a question like this, and it only asks about the new moon or the full moon, you can boil it down to this. Is the moon between me and the sun, or is it on the other side of the sun from me, on the earth? So the new moon is between us and the sun, right? The earth and the sun. The full moon is on the other side of the earth from the sun. So if it's between the sun and the earth, like the new moon, it's moving with the sun. It's going to rise at sunset and rise at sunrise and set at sunset. Does that make sense? If it's between us and the sun, then it's going to rise at the same time as the sun and set at the same time as the sun. If it's on the other side of us from the sun, then it's doing the opposite. When the sun goes down, the moon comes up. When the sun goes up, the moon comes down. Does that make sense? So for this one, you could draw out that whole thing and do that. Or you could think, okay, so it's a full moon, which means it's on the opposite side of the earth from the sun. So it's doing the opposite of what the sun is doing. When the sun is rising, the moon is setting. When the sun is setting, the moon is rising. Okay? Which of the following statements are true and which are false regarding radio waves and visible light? So So both are a form of electromagnetic radiation.
True.
That's true. Light and electromagnetic radiation are, all light is electromagnetic radiation. Radio waves travel faster than visible light because of the longer wavelength in a vacuum. That's false. All light travels at the same speed. Doesn't matter what type of light it is, it travels at the speed of light. Radio waves have a longer wavelength than visible light radiation.
True.
That is true. Radio is down here. This has a long wavelength than what's right here. And then radio waves can travel through a vacuum. Visible light requires an atmosphere to be transmitted.
False.
That's false. All light can travel through a vacuum. Some light doesn't travel through atmospheres because it gets absorbed. But that depends on what your atmosphere is made of, right? Because different elements absorb different wavelengths, so different types of light. But all light can travel through a vacuum. So consider a 1 meter radius solid copper sphere heated to 100 C and a 1 meter radius solid gold sphere heated to 100 C. And then we're going to label the following true or false. So, just first of all, before we go into the true or false, just think about this kind of conceptually. On this plot here that talks about temperature and wavelength and brightness, is there anything in there about what this object is made of? Aside from, is it a hot gas? Right. So that tells you that as long as we're not talking about hot gases, we're talking about hot solids or hot plasmas or whatever, then anything at the same temperature is going to give you the same curve. Right? It doesn't matter what it's made of. It's going to give you, the only thing that matters is the temperature. So, this says, the first one is the copper sphere will produce radiation at shorter wavelengths, which are higher energies. So shorter wavelengths are higher energies, but will the copper sphere produce radiation that is shorter than the other sphere? No, it's going to produce the same radiation. The copper sphere will produce more total electromagnetic radiation. Again, no, it's going to produce the same radiation. The two spheres will produce identical emission line spectra.
False.
That's false. They are continuous spectra. Emission line spectra is for hot gases. Yeah?
What does the emission line spectrum look like?
And so, in a form like that,
Yeah.
so it looks like this. Right? So I've got my wavelength and my brightness or intensity, and it's only giving off light in these really specific wavelengths and then no light in the other wavelengths. So, there's something above 0 for every wavelength, but this one only gives off light in these ones and no light in those. So that one specifically would have 4 peaks, right? Because there's 4 lines. So we look, something like that.
And that's for a hot gas.
This is a hot gas.
And the plank is for everything else.
Yeah.
And what is the difference? Sorry, what is the difference between a spectrum and a spectra? Or is it something?
Spectrum is one, spectra is plural.
Okay.
So if I'm just talking about the specific spectrum of one thing, or if I'm talking about spectra in general. Yeah, it's just singular and plural. So they will produce continuous spectrum. And then the gold sphere will produce a distinctive emission line spectrum.
False.
And that's also false. Again, it's going to be continuous. So you guys don't really need to know, don't worry about these absorption line spectrums. You don't need to know. You just need to know continuous and emission line. I just kind of like to fit that piece of the absorption line spectrum in because it makes sense to me that if you merge these two together, you get this, right? If I just slotted that in. So this, I took specific wavelengths out, and that's what I'm left with. And that's here. But you don't really need to know anything about that. Just the important thing is hot gas emission line, hot everything else, continuous. Mercury's surface has a high density of impact craters. This is because, so I guess I didn't really talk about this, but, so there's essentially no atmosphere on Mercury, so I did say that, right? So Mercury doesn't have an atmosphere, which means when a crater, something hits the surface and makes a crater, it just stays there. There's no weathering, there's no wind that blows it, there's no like atmosphere that changes how this crater looks. There's no volcanic or tectonic activity resurfacing on Mercury. That is true. Mercury doesn't have, on Earth, we've got the mantle moving under the crust. It moves things around. The crust is shifting and changing shape because of volcanic activity, and that changes how craters are. Mercury doesn't have that. There's a much higher density of asteroids near Mercury because it's close to the sun. That is not true. The most asteroids are between Mars and Jupiter in the asteroid belt, and then out past Neptune in the Kuiper belt. There are asteroids in other places, but there's not more near Mercury. And then the last is Mercury's surface is metallic and easily fractured, and that's not true. Mercury is a rocky planet.
But it is easily fractured.
Not in the sense that like a rock can kind of break up, but it doesn't like fracture. It's not metallic.
Right.
And then the last one says the emission line spectrum of each element in a gas state shows a unique pattern of wavelengths. So that's this unique pattern. This. Which of the following statements best understates the underlying physical reason for that? Why does this happen? Why does it only absorb specific and re-emit specific wavelengths of light? Right. There's only each one, the electrons can only take just the right amount of energy to jump up to the next orbital level. Each type of atom has a different height to that orbital level. So each electron in the different atom has to get a different amount of energy. Different energy means different wavelength. Okay, so that is quiz 1. You guys have any questions? Anything you want me to go over? You feel good on this stuff? How you guys doing? Okay.
I'm still kind of confused on 8 as to why the two spheres will produce, or why won't the two spheres produce identical emission line spectra?
So because they're continuous spectra.
And what is the relevance of that? Like, to say something's continuous?
So it means that it's putting off light in every wavelength. So this spectrum here, every wavelength it's putting off some light.
And how do we know that the two spheres would give off
Continuous versus emission?
Yeah.
Because they're not hot gases.
Oh, okay.
So like you separate, if something is hot, you say, is it a hot gas or is it something else? If it's a hot gas, it's emission line. If it's something else, it's continuous.
Okay, cool. Thank you.
Yeah. Any more questions on quiz 1 stuff? All right. We will move on to quiz 2. Let me just check. I'm going to quickly check on the Zoom people. Zoom people, you doing okay? Make sure this is still recording. Good enough. Okay, cool. You guys are able to see everything and follow stuff? Awesome. All right, then we will get back to it. Okay, so moving on to stars. So some important properties of stars. Luminosity. This is one of the most important things about stars. It is intrinsic to a star, and it is the amount of energy or light that is produced by that star and sent out. So luminosity does not depend on the observer. This star doesn't care who's watching it when it makes its light and sends it out, right? It's just how much light is made by the star. Very closely tied in with luminosity is brightness. Brightness is how much light we, as an observer, receive from the star. So brightness changes with distance. If you are farther away from a star, you are going to get less light from that star than if you were closer in. But the luminosity stays the same. The star is putting off the same amount of energy no matter how far away the observer is. But how much energy that observer actually gets changes. So I've used this example before, but it's like if you have a 60-watt light bulb, it's a 60-watt light bulb no matter what. If it's right in front of you, it's going to look really bright. If it's all the way across the room, it's going to look not as bright. But that didn't change that it's a 60-watt light bulb. 60 watts is a luminosity. If I put a lampshade on that, it looks less bright, but it's still a 60-watt light bulb. So brightness changes with distance, and it can also change with if there's like dust between us and a star. That can make it look dimmer. But, hi Dave. What's up?
These are quiz 4.
Oh, okay.
I'm just gonna put them here.
I left mine in my office.
Oh, okay. Well.
Do you want to grab them for me?
Okay.
Okay, they're just on my desk in the cat folder.
Yeah.
It's a folder with like cats with like
Yes.
in spacesuits on it. Huh? No, I got all the boxes here.
Oh, so what am I grabbing?
Just the folder of quiz 4.
Okay. Yeah.
It's on 255. Mine's the desk with all the stuff on it.
I'll be right back.
Thank you. Okay. Cool. So sorry. Where was? Okay. So luminosity stays the same no matter what. It's an intrinsic property of a star. Brightness changes with distance. Brightness is what we measure on Earth. We can't measure the luminosity. We don't know how much energy it's giving off. We can only measure how much energy we get. But we can use other things to figure out the luminosity. If we know how far away it is from us, and we know the brightness, then we can calculate how much it's been dimmed by that distance and figure out the luminosity. Okay? So the formula that we use for this is... Oh, I should have told him to get my other marker. Damn it. Where is... No, it's fine. I don't think I have...
Do you want me to check like a room or something and just snag a couple?
I think it's... Can you guys see this well enough? Okay.
Yeah.
So, luminosity is proportional to the brightness over your distance squared. So, if you have a star with a higher luminosity at the same distance, it's going to be brighter. Like two stars, one has a bigger luminosity, they're the same distance, it's going to be brighter. If you have a star that is at the same brightness and the same distance, then you know that the brighter one is more luminous. So when distance comes into play, if you have two stars that are at the same luminosity, but one is farther away, the brightness will be less, right? So if your distance to a star goes up, if we have a star and it's a certain luminosity and we see it as bright and we move farther away from that star, the brightness is going to go down. So if distance goes up, luminosity stays the same, brightness goes down. Okay, and luminosity changes faster because it's this distance squared. If you double the distance, luminosity is, if it's the same brightness, double the distance, luminosity is going to go down by 2 squared, so 4. So this is get like bigger distance, same brightness, smaller luminosity. Same luminosity, at bigger distance, then the one with a bigger distance is going to be less bright. So then we have radius. This is the physical size of something. Mass is like how much it weighs, how much matter is in that physical size. So it's pretty common if you have more mass that you'll have a bigger radius, but it's not always true. You can have something that is really big but doesn't weigh very much. If I have a big ball of styrofoam and a small ball of lead, that lead is more dense and it's going to weigh more than my ball of styrofoam, even though it has a smaller radius. So the trend is for bigger radius, bigger mass, but it's not like a hard rule because it depends on the density. So radius is the physical size, mass is kind of how much it weighs. Surface temperature, this is just the temperature at the surface of a star. Thank you so much.
Yep, there you go.
You're the best.
Cheers.
Okay, so again, this is my Cats in Space folder that I've kept all your quizzes in. Chemical composition, this is like what the star is made of. Like I said, they're mostly hydrogen and helium, but the other elements are important, and they make up what the star is made of. They can change its behavior. And then distance, this is not like technically a property of the star, but it's, a relation between us and the star. So, these are some properties, some ways we measure them, and some values. Distance, we measure something called trigonometric parallax. Stars are between 1.3 parsecs to 100 parsecs. That's like in the Milky Way. Obviously, there's stars that are much farther away from that in other galaxies. Surface temperature. So we determine this from color or spectral type. So just like we talked about, Wien's law, that formula that said temperature is equal to 0.29 over the peak wavelength. If we say, okay, well, I know what color it is, what peak wavelength it is, then I can get my temperature, right? Luminosity, so if I can measure the distance with the parallax or with something else, and I can measure how bright it is, just with like, a CCD or a telescope or sort of instrument on Earth, then I can use this formula, I can do brightness and distance, and I can get my luminosity out. Radius is from something called Stephan's law, and this is tells us that energy per surface area is proportional to sigma. This is a constant times t to the fourth. So energy, that's our luminosity, right? So this is our luminosity. Temperature, we can measure. Luminosity, we can measure with this. Sigma is just a number. It's just a constant. So then what's left is surface area. For a sphere, your surface area is 4 pi r cubed. So you get your radius. Right, so this is Stephan's law.
Are we gonna have to, or are we gonna be expected to be able to apply Stephan's law? Yes.
You weren't on the last quiz. You were just expected to be able to know what we use it for. Right. And I gave it to you on the quiz, so if you didn't know automatically, you could look and say, okay, what do I have? What can I solve for that? If I know surface area, then I know the radius. Yep.
Are we gonna be given equations in final?
Sure. Yeah. And then mass and just the laws of gravity are another. For surface temperatures, they can go between 3,000 Kelvin to 50,000 Kelvin. Distance and brightness, stars can be 1 times 10 to the negative fifth the luminosity of the sun, all the way to like 1,000,000 times the luminosity of the sun. Stephen's law, they can go from 0.01 times the radius of the sun to about 800 times the radius of the sun. So we looked at that picture of like the solar system with our giant sun and all our tiny planets, and then some stars are 800 times. The radius is 800 times more, and yeah, so surface area, surface area goes up as radius squared, volume goes up as radius cubed. So if the radius goes up by 800, the volume goes up by 800 cubed. So it's like that much bigger in volume than the sun. And then mass, the limits are between 0.08 solar masses to, this says 80, we sometimes say 100, but in that range of 80 to 100 solar masses. So some of these techniques, parallax. This is the apparent change in location of a star relative to the background when you're observed from 2 different locations. So this is this idea, like if I'm standing right here and I say, like, where is my laptop? And it is, to me, between you 2 guys in this front row, right? If I move over here and I say, where is my laptop? Now it's between you guys. My laptop didn't move. I moved, and my laptop looks like it's in a different spot compared to you guys. So that's this idea of parallax. And if I measure how far my laptop looked like it moved, because so right now I can see distance, right? I can tell that my laptop is closer than you guys are. But when we're talking about stars, they all look like they're the same distance away, right? So if I collapse this down, then it's all just kind of in a line. So if I know how far my laptop looked to move, then I can tell how far away it is from me. So this formula, distance is equal to 1 over your pi is your parallax angle. So as parallax goes up, distance goes down. And parallax is how much it looked like it moved, right? It looked like it was over there, and then it looked like it was over there. So that's my parallax angle. If you have a bigger parallax angle, it's closer to you, right? If I'm standing right here, it looks like it went from you guys to you guys versus these first 2 to these first 2.
Is distance in parsecs?
Yes, this distance is in parsecs. And then this is in arc seconds. So if you kind of forget, you can look at the equation and see that they are inversely proportional to each other. Or you can also just test it out with your thumb. Because your eyes are in 2 different locations. So if I put my thumb right here and I blink, it looks like it moves. If my thumb is farther away, it looks like it moves less than when it's close up. You can always test that and see. If it looks like it moves more, it's closer to you. And I did Stephen's law. Binary stars, this is if you have 2 stars that are orbiting around, they're really orbiting around their common center of mass, which is something I talk about later and went over in some sections. We can measure how fast they're orbiting and get their masses from that. And this is like a graph of the 2 stars, their speed versus time. The one with a bigger, higher curve is going to be the less massive star. The one with a smaller curve is going to be the more massive star. So if it's a more massive star, it's bigger, it's kind of harder to move, so it's not going to go as fast. right? The smaller, lighter star is going to go faster. So we measure masses from that, and then just generally from the laws of gravity. The structure of stars, kind of in general. The big idea in stars, for most stars, is this idea of hydrostatic equilibrium. So gravity pulls everything inwards. If there were nothing to push back against gravity, then the star would just collapse. So something has to push back. And that thing that's pushing back is this thermal pressure or gas pressure, right? It has to be a balance between the two. The pull of gravity has to be equal to the push of the gas pressure. If the gas pressure is more, the star will expand. If the gravity is more, the star will collapse. They have to be just equal to each other for the star to stay the same size. Temperature, density, and pressure all increase as you go towards the center of a star. So that's this graph over here. You can just see its density on top and temperature on bottom. As you get closer into the star, those go up. So the hottest place in the star is the core. So when we look at a star and we look at its color and measure its temperature from that, we're seeing the surface temperature. Right, and that's different from the core temperature. The core is going to be a lot hotter than that surface temperature. The surface temperature of the sun is 5,700 Kelvin, and the core temperature is over 10 million Kelvin. So, the power source for stars. Stars are powered by nuclear fusion. You have two atoms or two nuclei coming together to make something new. So the most common one is you have two hydrogen atoms, which are have one proton each, and those come together and make a new nucleus, which is the helium atom, which has two protons. Right? So the number of protons in the nucleus is what determines what element it is. You can have different numbers of neutrons and have it be the same element. You can have different numbers of electrons orbiting it and have it be the same element. The thing that determines what element it is how many protons it has. So when I take these two protons and I put them together and make a new nucleus with two protons in it, that's a new element, that's helium. So the product has less mass than the sum of the two that went in. If I take those two helium, or those two hydrogens, and I weigh them, and then I put them together to make that helium, and I weigh that helium, it's going to weigh less than the sum of those two hydrogens. And that missing mass got turned into energy. With that formula, E equals mc squared. E is energy, m is mass, c is the speed of light. So you can, if you know how much mass got turned into energy, or if you know how much mass disappeared, then you can calculate how much energy got released when this fusion happened. So this energy, that's the power for the star, and that's the source of light. Light is a form of energy. So as the temperature in that core increases, fusion happens generally in the core of stars, and sometimes in shells around the core. As the temperature increases, bigger atoms can undergo fusion. So at first, if you're at a certain temperature, if you're at 10 to the 7, so 10 million Kelvin, hydrogen can fuse into helium. If you get hotter, like 10 to the 15 Kelvin, then helium can come together and fuse to make beryllium. If you get hotter than that, helium and a hydrogen can come together. Lithium happens first, but that burns up really quickly. You can get that beryllium, and then you can make oxygen or carbon and oxygen and neon and silicon and so on. So the bigger thing that you are fusing, the hotter it has to be. So bigger, by bigger I mean more protons higher up on the periodic table. The more massive the star, the hotter the central temperature. So a more massive star can fuse heavier things in its core. It gets hotter, it can fuse heavier things. If a star is below, or a gas cloud that's collapsing to make a star, is below 0.08 solar masses, the temperature is never going to get hot enough to start fusion. So that's why there's this lower mass limit to stars. It has to be massive enough that the temperature in the core can get hot enough to start fusing stars, because stars have fusion. Like, that's what separates like a brown dwarf or a gas giant like Jupiter from a star, is that there's no fusion in those, and the star has fusion.
Would Jupiter be large enough to be a star?
No, it's not massive enough because it doesn't, and so it can't have fusion.
Okay.
Above, 80 to 100 solar masses, then the gravity just can't hold against that outward pressure, and the star just has these big stellar winds, and it just blows off material. So that's why that's kind of the upper limit. There's something called the main sequence. This is the time in a star's life that it is burning hydrogen into helium in its core. So stars start off with mostly hydrogen and some helium and some other stuff. And in its core, it gets hot enough, and it's burning hydrogen into helium. And the time that it's doing that is called the main sequence. It's time on the main sequence. The main sequence is all of the different stars that are burning hydrogen into helium. So this is called the Hertzsprung-Russell diagram, or the HR diagram. This is not the life cycle of a star. This is if I took a picture of the sky and I sorted all the different stars by temperature and luminosity, I would get this. This is all different stars. Okay? So this big diagonal line here, this is the main sequence. All of these stars along it are burning hydrogen into helium in their cores. Okay? Some important things to note. So it's a little weird in that temperature goes up in this direction. Normally, we're used to axes increasing in that direction. Temperature increases towards me. Luminosity increases up. So the hottest stars are on this side. The most luminous stars are up on the top. Radius increases kind of diagonally this way. So the stars with the biggest radius are going to be up in that corner over there. On the main sequence, mass increases this way, towards this one. So the most massive stars are up in this corner. So if I kind of draw just the trends out, instead of drawing the stars, I've got my main sequence. Temperature increases this way, luminosity increases this way, radius goes up this way, and mass goes up this way, right? So we've got an X, radius going up one way, and mass going up the other way. So when I said that there's, it's kind of related, stars down here are going to have a small radius and a small mass. Stars up here are going to have a big radius and a big mass, but the most massive stars do not have the biggest radius, necessarily. Yeah.
One thing that I wondered about a little bit is, so when a star moves off the main sequence and starts fusing
Helium?
more other elements,
Yes.
even past helium, if they're these ones here, they're still like less hot, right?
Mm-hmm.
Is the reason that they're hotter in their core based on kind of being insulated?
So this measures surface temperature, right? So this is surface temperature. So the reason that they get hotter in their core is because their core contracts and their outer layers expand. So as that core contracts, it gets hotter. The core gets smaller and gets hotter, and the outer layers puff up and cool down. Okay. So a star is born on the main sequence. Like that's the first thing that happens is it collapses down from this gas cloud, collapses down to form a star, and it starts fusing hydrogen in its core, and that's when it becomes a star. And it's the stars that are fusing hydrogen in their core on the main sequence, so we say a star is born on the main sequence. And it lives its whole time that it's fusing that hydrogen in basically the same spot. It gets a little bit more luminous during that time, but it doesn't, we move a little bit. But it's not going to move, it doesn't move up this way. It just gets maybe a little bit more luminous. But it's essentially in kind of the same spot. And then the more massive a star is, the less time it will spend on the main sequence. So more massive stars have more hydrogen fuel to burn, but they burn it faster. They're like gas guzzlers. They just go through their fuel super fast, and they run out of hydrogen faster than these little efficient low mass stars. So lifetime also goes, lifetime and mass on the main sequence are inversely related. So this is time on the main sequence. Right, so the sun is going to spend about 10 to the 10, so like 10 billion years on the main sequence. We're about halfway through its time on the main sequence. A star with less mass than the sun is going to spend longer on the main sequence than the sun does. A star with more mass is going to spend less time. So these stars up here, they may only last 10 million years on the main sequence. These stars are going to last a lot longer. We've got our main sequence. Then there is, over here, your giants and your supergiants. And then down here are the white dwarfs. These are hot and small. Those are big and radially large and have cooler surface temperatures.
Do the blue supergiants they don't have cooler surface temperatures?
They are cooler than like these white dwarfs.
Okay.
They're hotter than the red supergiants,
Okay.
but they're still cooler than, they're still on like that half.
And then just to
Something about-
reiterate, if they're hotter, they don't necessarily have a higher mass?
Right.
Or,
So generally, if you are in the same stage, if you're hotter, you'll have a higher mass. So if you're both main sequence stars, then the higher mass one will be hotter.
okay.
If you're both giant stars, then generally the higher mass one will be hotter. But you can't necessarily compare a main sequence star to a giant star
Okay.
and say that.
Thank you.
Yeah, it's a lot easier to compare stars within like the same type than it is to compare across types. So, like I said, a star stays mostly in its life on the main sequence, and then when it finishes up its hydrogen fuel and starts to do other stuff, it moves off diagonally like this and goes and becomes a giant. Or these guys go and become supergiants.
Okay. Cool. Thank you.
So, stellar life cycle, we split this into two branches. You have smaller stars or smaller. When I say smaller, in this case, I mean less massive, and then more massive stars. And that limit between the two is about 8 solar masses. So these less massive stars, those are going to be between 0.08 solar masses, because that's the lower limit, to about 8 solar masses. These massive stars are going to be about 8 to 100 solar masses.
What was I'm sorry, the lowest value? What was that?
0.08 solar masses. Below that, it never gets hot enough to fuse hydrogen and won't become a star.
So once they become like the low mass star, they become like a white dwarf.
That's the end stage of it, yeah. So I'm going to kind of go through these two tracks. So they both start off as a cloud of gas that collapses down to form a star. And then they both have their main sequence time, the time they spend burning hydrogen to helium in their cores. And this guy's going to have a shorter time on the main sequence than this guy. So going for this small star, when he fuses all the helium or the hydrogen into helium in his core, then he sort of runs out of fuel for a second. Not really, but it kind of works this way. So gravity starts to win out because the thermal pressure is not being generated to push back. So it starts to collapse. And the core gets denser. And as that core gets denser, it heats up. Because when things get denser, they get hotter. And as it heats up, all of a sudden, it's now able to fuse helium. And so the fusion, starts back up. This happens kind of in a gradual thing. It's not like it turns off and then it collapses and turns up, but it's kind of a gradient. But helium starts to be able to be burned in the core. And then as the helium, so the core gets hotter, right? Here's our star. It used to be you have hydrogen going to helium in the core. And then now all this core has been turned into helium and you have hydrogen out here. And this core got hotter. So the part on the outside got hotter too. And this core got hot enough to burn helium. And then this part that's filled with hydrogen is now hot enough to burn hydrogen into helium. And then as this gets hot, so then when this runs out of helium, then it can burn carbon. And now this is filled with helium. So this starts to be able to burn helium. And this part out here with hydrogen now gets hot enough to burn hydrogen into helium. So you get these shells, right? As the core gets hotter and can burn newer things, then the next shell out, the ashes of that shell are now hot enough to start to burn. And another shell on the outside starts to burn. So you get this kind of onion structure. In a low mass star, you can burn all the way up to carbon and oxygen in their core. And then it just can't there's not enough mass for it to get hotter. It can't collapse down anymore. It can't get any hotter. And it can't burn it. There's no more fusion, so fusion turns off. And it can't collapse anymore, we said, because it's already as dense as it can be. And the outer layers start to just drift away. And this is called the planetary nebula phase. So I've gone less mass, or small mass star. It went into the red giant phase. Oh, sorry. When the core contracts and starts to burn helium, the outer layers puff out and cool down. So the core gets hotter, but these outer layers are farther away, so they get cooler. So the surface gets cooler, but the core gets hotter, and the star increases in radius. So when the sun turns into its red giant phase, it's going to puff all the way out, basically to the orbit of the Earth. Yeah.
So luminosity is based on core temperature, kind of.
Yeah.
But the heat on that other diagram is based on
The surface temperature. Right.
So that's why a red giant gets more luminous,
Right.
but less hot.
Right.
Slightly as
Yes.
it moves up from each other.
Exactly. The core gets hotter, so it can do more fusion, and you can have fusion in those rings. But the outer layers cool down. Yes, you were exactly on about that.
Miranda?
Yeah.
Really quickly,
Mhm.
why does the star need to be over 0.8 solar masses?
Because if it's less than that, the core will never get dense enough to get hot enough to start fusion.
Okay, so it just won't become a star.
Right. It can still collapse down, but it won't become a star. It'll become a brown dwarf, or if it's smaller than that, it'll become a planet. Okay. So these outer layers, they've puffed up into the red giant phase, and then after this planetary nebula phase, now they're just floating off into space, and it makes these really pretty gas clouds. And what's left is that core, right? All these outer layers floated off, and what's left is this core that is not having any more fusion, but it's really, really hot. There's not anything to keep it hot anymore, so over time it's going to cool off, but it starts out super hot. Right? It starts out hotter than the core was originally when it was in the main sequence. And that core, that is the white dwarf that's left. And they are made up of, like helium, carbon, oxygen, depending on how big the star was initially. And the biggest a white dwarf can be is 1.4 solar masses. Because, so I said before, like in normal stars, the hydrostatic equilibrium, you have gravity pulling in, and then fusion creates heat and energy that pushes back out. So this white dwarf isn't fusing, so there's no, there's not that fusion to push back out against gravity. So something else has to push against gravity, and that is called electron degeneracy pressure. So electron degeneracy pressure can only push back against 1.4 solar masses worth of gravity. So that's the limit for a white dwarf. So going back to this HR diagram, you have your solar mass or less, or up to 8 solar mass star. It lives its life on the main sequence. Then it goes up into the giant phase, and then as these outer layers shed away, that hot core is revealed. So the luminosity comes from that core. So the luminosity is going to stay the same, and the temperature increases as that hot core is revealed, as these outer layers float off into space. And so the planetary nebula phase is this straight kind of line across here. And then we have that hot core, and then it just cools down like that. Right? It cools down as there's nothing keeping it hot anymore. It's just a coal left in the sky. And it's cool, like I said, some of them are made of carbon. They're basically just giant diamonds out in the sky for these carbon white dwarfs. So that is low mass stars. Gets a little bit more exciting. Oh yeah. Do you have a question?
Oh, yeah.
Yeah.
Can you explain electron degeneracy?
Yeah. So this is the force that is pushing up against gravity in a white dwarf, and it's, in order to really understand what electron degeneracy pressure is, you have to understand some quantum mechanics stuff, and I'm not going to really go into that. But the way that I like to think about it, which is not what's actually happening, but what helps me visualize it, is kind of, at this point, the atoms, you have your atoms with the nucleus and the electrons going around. The atoms are basically just pressed up against each other. I think you call them marbles. If you have a bag of marbles and you're squeezing it, at some point you can't squeeze anymore because the marbles are all up against the edges of each other. So these electrons are pushed up against the edge of each other. Right? So it's electron degeneracy pressure. It really has to do with electron energy states and how you can't have 2 electrons in the same energy state. Because of the Pauli exclusion principle, but it's weird. Quantum mechanics is really weird. no, my quantum mechanics textbook, like the first page, it had this quote that was like, if you think you understand quantum mechanics, you're wrong. So, I have a degree in physics. I have no clue what's going on in quantum mechanics. So that's kind of, this is how I like to think of electron degeneracy pressure. This is how I kind of helps me understand, in a sense, what's going on. And, I can remember it's electron degeneracy pressure because the electrons, these outside of these atoms, are kind of rubbing up against each other.
And the way I've also memorized it is that if it's not neutron degeneracy, then it's electron
Right.
degeneracy, and neutron degeneracy goes with the neutron star on the bottom branch.
So if you can kind of do that process of elimination, there's electron degeneracy pressure and neutron degeneracy pressure. Neutron goes with neutron stars.
Is the planetary nebula just like the in-between phase?
Yeah. So in the middle of this planetary nebula is this white dwarf. And the outer part is this outer part of this star. And it's just the part where the outer layers are floating off and that core white dwarf is starting to become exposed.
Does that happen during electron degeneracy?
So in the middle of that core is held up by electron degeneracy pressure. And then the outer layers are not held up by anything. They're floating, or they'll just be pushed away.
What
And
happens
floating.
after
It just cooled off, like forever, essentially. So one thing is that white dwarfs cool off, and we've never found a white dwarf below a certain temperature. And the reason for this is, there's a finite age to the galaxy and the universe. So our galaxy was formed, and the stars were born and lived their life. Oh my god. Okay, I had some video, man. I didn't do it. So the stars were born, and they lived their life, and they, did their giant to planetary nebula to white dwarf, and now they're cooling off. And there just hasn't been enough time for any white dwarf to cool off more than this, like since the stars were made.
So you know how hot that shit is.
Yeah. So we've never found anything cooler than that because there's just not enough time. And so when this white dwarf first becomes revealed, it's hotter than it was originally. Like, it's hotter than it was originally. We were measuring the surface temperature over here, and then the core temperature went up and up and up and up, and now we've revealed that core. And that core temperature is kind of our new surface temperature for the white dwarf. So it starts off hotter than the original star was, and then goes down.
Okay, I'm just gonna your laptop's about to die.
Oh my gosh. Oh, thank you. Okay. Good call. That would be terrible. Wait, I got my...
Are you having to restart the video? The recording?
No, I'm not.
Get
Because...
it out?
Okay, so the thing is, so if you are a student, then you have that 40-minute time limit. But professors don't have a time limit, so I just had my advisor make a Zoom meeting. And I'm using that.
Nice.
But I can't record somebody else's Zoom meeting unless they're in the Zoom meeting, which is why I'm recording it on Photo Booth. And not Zoom. Okay. Thank you for that. That would have been kink in our plans. Okay. So are we good on low mass stars?
Mm-hmm.
Okay. So we're,
Sorry, just
No, it's fine.
It helps me remember. So 0.08 to 8, and then 8 and above is massive.
yes.
I think 8 to 80 or what?
Yeah, so if you can think of it 8 to 80. 0.08 to 8, 8 to 80.
Oh wow. Okay.
Right? You just move that 0. It's 0.08, flip it to the other side, you get 80. Okay, so these massive stars, they kind of do the same thing at first. They have their main sequence time. They're burning hydrogen to helium in their cores. And then they become a red giant, or because they're bigger, they become a supergiant. And I said here, so we've got a similar thing that's going on where they're having this core burning and then the shell. So the core burns something, and then it gets hotter, so it can burn the next thing. And the shell outside of it has heated up, and it can burn something. Then when it heats up more, those ashes can start to burn. Or when I say burn, I mean fuse, right? When I say burning hydrogen, that means fusing hydrogen. Burning helium means fusing helium. So, in a less massive star, we can't really fuse much beyond carbon or oxygen in the core. It just doesn't get hot enough. But if you have more mass, you can get hotter and you can fuse more. You can fuse oxygen to magnesium, to silicon, to neon, all the way up to iron in the core. And iron can't fuse anymore. These are equilibrium fusion reactions, and iron is where it ends. It is like the peak of this. If you want to fuse iron, it takes energy instead of releasing energy. For everything else, when we fused it, it released energy. Past iron, it will take energy to fuse them. So this star is not going to use up its energy to fuse. It uses fusion as its energy source. So for a massive star, you get something like this with all these shells. Right? You have on the outside is the hydrogen that hasn't gotten hot enough. The most outer shell is hydrogen burning to helium, and you have helium burning to carbon, carbon burning to oxygen, oxygen burning to neon, neon to magnesium, magnesium to silicon, silicon to iron. And then the iron just builds up in the core because it's not going to fuse. So it's the heaviest. It sinks down into the core, and it just builds up until you get to, again, 1.4 solar masses of that iron core. And then the gravity, or the iron core can't hold itself up anymore against the gravity. And it starts to collapse. And when it collapses, again, not necessarily what happens, but the way I like to think about this is these atoms that used to be kind of like pressing against, their outsides are pressing against each other, now they get broken up into pieces and they can press together even more. So if we're talking about like marbles, if you crush up all those marbles and squeeze them together, it's going to be smaller than just the marbles were. So if you squeeze and they break into pieces, then you can get them tighter, right? So it's able to collapse down past that electron degeneracy pressure, and then the thing that stops that is called neutron degeneracy pressure. So you break it down, instead of being atoms, it's broken down into its little pieces, its neutrons and stuff, and then now those neutrons are pushed up against each other. And you have a bunch of neutrons. Yeah.
So both are the Chandrasekhar limit. Both are the 1.4
Mm-hmm.
mass of the sun. But the smaller stars are just kind of at this white dwarf phase. So is that kind of where is that why they're divided? Is because essentially anything that's 8 solar mass won't really end up as a larger white dwarf than the 1.4 solar mass?
Right. Once you get past that, then you get hot enough to fuse these other things in the core, and it moves past the white dwarf stuff. So, like, once you get past that, like, carbon and oxygen and stuff, you can get some magnesium, but you can't have, like, an iron white dwarf.
But so we're essentially saying what we know about the 0.08 to 8 is that branch really never exceeds the 1.4 at the end.
Right. It can't. The white dwarf can't hold itself up.
Right.
So that's how we get supernova type 1 later on. Like, that core will reach equilibrium at 1.4. You can have white dwarfs less than 1.4.
Right.
But if you get more than 1.4, then it's going to be able to collapse down more and fuse more.
What does the 1.4 mass mean?
So 1.4 is both the mass limit for a white dwarf. It's the biggest a white dwarf can be, and it is also the limit of the iron core inside of a red supergiant. So once that iron core reaches that 1.4 solar mass limit, then it's going to collapse down. And this collapse down it collapses down super fast, like fractions of a second. It goes from being this big iron core into being very, very small. And when that happens, all of the gas, the outer layers of the star, rush in, they hit this super dense core, and they bounce back out. And they rushed in really fast, they hit the core, they go out really fast in a big explosion. And that is our supernova type 2. It's these outer layers exploding away after this core collapse. So, if you are at under a certain limit, like if your core thing is only under like 3 solar masses, then what you are left with is that neutron star. That core collapses down, these atoms kind of break apart until the neutrons are pressed up against each other, that neutron degeneracy pressure, and you have a neutron star. If you have more mass than that, if stuff falls back in on that neutron star and it grows, then that neutron degeneracy pressure can't hold it up anymore, and it's going to collapse even more. There's nothing past neutron degeneracy pressure to push back against gravity, and it's just going to collapse all the way down till it's just a single point, and that's our black holes. So, white dwarf, electron degeneracy pressure, neutron star, neutron degeneracy pressure. Okay, so these are our 2 tracks for the stellar life cycle. You guys feel okay? Kind of went over this already. Okay, that's it for quiz 2. So, problem 1 says, which of the following best describes the technique used to determine the radius of a star? So, the options are measure the apparent size of the star, then make a 1 over distance squared correction for the distance. Is it easy to like look up at a star and measure how wide it is? No. Measure the wavelength at which the radiation from the star is the greatest and use parallax for the distance measurement. So wavelength tells us what? That peak wavelength tells us what?
The color? No.
The color. I mean, it does tell us the color, and from color we learn temperature. So temperature and distance, is that going to give us radius? No. Measure the surface temperature and luminosity of the star, and then use Stephan's law for radiation per unit surface area. So that says, radiation is your luminosity per surface area. You can say, I know surface area and radius are related. So if I need surface temperature and luminosity, I guess Stephan's law is radiation or energy per surface area proportional to sigma t to the 4th. So luminosity gives me this. Surface temperature gives me that. Then I can get my surface area, and then get my radius. So use Stephan's law.
Is that how is Stephan's law written, by the way, or is that how it's written?
Like this.
Oh, okay. For sure.
Radiation or this maybe energy.
Okay. Oh, okay. And then what's the sigma? Or-
Sigma. It's just a constant. It's just a number. Just like pi is like 3.14. Sigma it's a number.
So this is the right answer?
Yes.
Okay. Okay.
So the last one says measure the apparent brightness of a star and use the luminosity to solve for the area of the star, then divide by 2 pi. We don't do anything like that. Luminosity and brightness give us distance. Is it okay if I skip these math ones? There's a video online about the trigonometric parallax ones, and they just take a little while, so I kind of want to go over the concept ones more. The sun will eventually go through which of the following phases? So the sun is a low mass or high mass star?
Low mass.
Right. So then this says planetary nebula, red giant branch. Is it going to go through that one? Yeah. Main sequence,
Uh-huh.
Yeah, so this question was a little confusing because people said, eventually go through. It's on the main sequence currently, so we give you credit whether or not you checked that. But it was supposed to be yes. Like, that when we say eventually means at any point in its lifetime. And then white dwarf. The other...
I also had neutron stars.
Yeah, so the other version had neutron star as an option. Is the sun going to end up as a neutron star? No. Why is there a lower mass limit of about 0.08 solar masses for stars?
Because objects below this mass don't reach the core temperature of at least 10 to the 7th.
Right. They need more mass, higher core temperature. If you don't have enough mass to get up to at least 10 to the 7 Kelvin, you're never going to get hot enough to start fusion, and you won't become a star.
Why isn't it because electron degeneracy pressure prevents hydrogen fusion before this mass?
Electron degeneracy pressure doesn't come into play until you get to these, like white dwarfs. So this is just gas collapsing down. Which of the following are true and which are false? So the sun and other main sequence stars generate their luminosity through fusion reactions.
True.
So, yeah,
Oh, it's true.
it's true.
Oh, never mind.
The other version said fission reactions. So fission is an atom. Fusion is two atoms coming together to make a new atom. Fusion is two atoms coming together to make a new atom. Fission is one atom breaking apart into two atoms. So in the sun, we have two things coming together to make a new one, so it's fusion. Then the sun is losing mass every day.
True.
That's true. So in the sun, that fusion is happening. We get the missing mass turns into energy and comes out as light. So all of the light that comes from the sun used to be mass. So the sun is losing mass every day. The fraction of the sun composed of helium is larger now than it was 1 billion years ago.
True.
That's true, because in the core of the sun, hydrogen is turning into helium. So over time, there's more helium in the sun. And then the luminosity of the sun decreases a small amount every day as it uses up its hydrogen fuel.
False.
That's false. It actually gets a tiny, tiny, tiny bit more luminous.
I have a question. Just about, I don't know if this is like one of those questions that you don't really like answer, you just memorize, but so not you, but like
Right.
that one memorizes.
Mhm.
So luminosity always stays the same, right? But like as it's burning different things, it stays this, like why does it not change?
So it does go up. The luminosity, so it stays the same on the main sequence as it's
Okay.
burning hydrogen into helium. When it goes, so when I look back at this,
So all of those are burning hydrogen into helium.
everything on here is burning hydrogen into helium in its core. So then as it goes into the red giant branch, the luminosity goes up, right? It goes off and up, so the luminosity increases
Okay.
as it goes into the red giant branch.
Thank you so much.
No problem. Yep. Oh, okay, so one version says smaller and one version says larger.
And it's larger.
It gets larger, right? The hydrogen is turning into helium, so there's more helium over time on the main sequence. Okay, did you have a question?
Oh no, I was gonna ask the same.
Okay. So then, which of the following are used in measuring stellar masses? So proper motion measurements of a nearby star. Proper motion is how much a star actually moves across the sky, right? We talked about parallax, which is how much it looks like it moves as I move, like around the sun or across this table. Proper motion is actually like stars really are moving through the galaxy. But they tell us how fast the star is moving transverse to us. Radial velocity measurements of stars in binary systems.
Yes.
That's true. That's that graph. Oh, no, I don't want that. Go away. What happened? Okay, sorry. That's this graph right here. These are the radial velocity measurements, and we measure mass with that. Red giants that are within 100 parsecs of the sun.
No.
That doesn't really have nothing to do with mass. Parsecs are a distance unit. And then Newton's laws of gravity.
Yes.
That teaches us about mass. So hydrostatic models for the sun or other stars are based on what?
The balancing force of gravity and gas.
Right. If you hear the word static, like in hydrostatic, that means not moving. And if things aren't moving, that means there's a balance somewhere. Right? If you have a scale and you put two things on it that aren't balanced, that scale's going to move. But if you balance it, it's going to stay where it is. Right? So if static is not moving, there's a balance. In this case, the balance is between gravity pulling in and thermal pressure or gas pressure pushing out. And then there's which of the following are true and which are false for the evolution of a star with 10 times the mass of the sun. So which track is this? Low mass stars massive stars. So a 10 solar mass star will fuse elements up to the mass of iron in its core.
True.
Right. Iron goes all the way, that's the end of it. A 10 solar mass star will end its life as a much more massive white dwarf compared to the white dwarf the sun will eventually become.
False.
Right. What's it going to end up as?
Neutron star.
The neutron star. 10 solar mass, I think,
Yeah.
is more.
Too small for a black hole.
Yeah, I think it's too small. A 10 solar mass star will explode as a supernova type 2.
True.
True. And then 10 solar mass stars are much more common in the galaxy than stars like the sun. That's something I didn't mention. These low mass stars are like much more common than high mass stars. Part of that is the reason because they're smaller, they don't need as much mass to start, but also they live a lot longer. So something that lives a long time, like if you're counting like things that burn up really quickly, you're not going to see as many of them when you look out as something that has a whole long lifetime. But there's a lot of factors that go into it, but there's a lot more low mass stars than high mass stars.
So
Yep.
more massive stars can either explode as a type 1 supernova or a type 2 supernova.
So type 1 supernova are a white dwarf supernova.
Okay.
So it's a completely separate type. If it's a massive star exploding, it's type 2.
But type 1s have to happen in a binary.
Yes, type 1s have that combined. I'll go over those next.
Mhm.
So supernova 2, which of the following support the theory of supernova 2 core collapse supernova? So supernova 2 are always seen near regions of star formation. This is true. They used to be stars, so they exist in areas where stars are born. The supernova remnants in the galaxy show evidence of heavy element enhancement. This is also true. All these elements that got formed here, when they exploded, they sent all those elements out in the supernova remnants. So when we measure the elements of what's in those remnants, it has these heavier elements. There are pulsars, which are rotating neutron stars at the center of some supernova 2 remnants. So that's true. I didn't really talk about this. So that neutron star is rotating really, really quickly. It has to do with something called the conservation of angular momentum, which is it's another balance. It's a balance between your radius and how fast you're rotating. If your radius goes down, how fast you're rotating goes up. So as this big rotating star collapses, it gets much smaller, so it rotates much faster. So these are rotating really quickly, and sometimes when you get these kind of like jets that come out of them. And if we are like standing right here looking at this, we're never going to see those jets because they're not directed at us. But if it's rotating, like this, then if I'm standing here, every once in a while I'm going to get a jet that's pointed straight at me. So I'm going to see this kind of like blinking, right? It's going to be nothing, and then a jet, and then nothing, and then a jet, and nothing, and a jet. So it's kind of like a lighthouse with the light turning. You get the light in front and then gone. And so they were pulsating stars, or pulsars. And that's basically all neutron stars are going to have this, but it's only when we're lined up with the jets that we see a pulsar. So it's just a special type of neutron star where we're actually lined up with the jets. And we know they have to be rotating really fast because of this concept, like all neutron stars should be rotating fast. We can measure how fast these are rotating because we can measure how fast the pulses go past us. And then they have luminosities similar to red giants. That's false. Supernova are much more luminous. They are like, some of them can be as bright as all the other stars in the galaxy combined. And the last one is again a math one that I do in the video. How are we doing on time? Okay. So, moving on. Are you guys ready to move on to quiz 3? You guys have any more questions on this stuff? Okay. So, that was one type of supernova. Now I'm going to talk about supernova type 1. So, when you have a white dwarf and a big star in a binary system, so they're orbiting around each other, a big star, and you have a little white dwarf. Sometimes the edges of this star, like if this star is expanding, the gas on the outer layers gets close enough to the white dwarf that it gets caught up in the white dwarf's gravity. And so it gets pulled away from this star and pulled onto the white dwarf. And this mass starts to build up on the white dwarf. And if the white dwarf gets enough mass that it gets bigger than that 1.4 solar mass limit, then that electron degeneracy can't hold it up anymore. And it collapses. And when it collapses, the temperature shoots up and you have like a runaway thermonuclear explosion. And this whole thing just explodes. And during that explosion, you can have something called a non-equilibrium fusion reaction. So all the fusion we talked about before is equilibrium fusion, and that's what goes up to iron. If you have non-equilibrium fusion in these white supernova type 1, then you can fuse up to radioactive nickel, which is like 2 spots up from iron.
And what's the difference? Like, I mean, that one is, like, what does that mean, the equilibrium part? Like,
So it has to do with like being able to go back and forth and like energy balance.
Okay.
I think it's just the important thing to know is that non-equilibrium only happens in these supernova type 1,
The supernova
and it's the
type,
only way you can get this nickel.
the supernova type 1 are the brightest things we see.
Yeah, they're very, very bright.
They're brighter than type 2? Or, okay.
I think it can depend. You might be right. I'm not super sure.
Because it's the supernova type 1 is what we use to
Right.
find
So
distances
we
to the
use them
galaxy.
specifically for distance because they are easy to calibrate. If we know how bright it is, like, so because they all happen the same way, then we kind of know how luminous this explosion should be.
Oh, got it.
So if we know how luminous they are and then we can measure their brightness, then we know the distance. So there's something we call a standard candle, where we know it's something we actually do know the luminosity of. And then when we measure brightness, we can measure distance. So we use these in other galaxies to measure distances to other galaxies, because there's something in another galaxy that's bright enough for us to see. We can measure its brightness, we know what its luminosity should be, and we can measure its distance. So if you measure the light from one of these supernova, you get a graph like this. And this right here is that big explosion. And then for a long time, we were like, why doesn't it just explode and then fade off? Like, where does all this light that's being produced come from? And it comes from this radioactive nickel that was produced in the explosion. That radioactive nickel decays to cobalt, which decays to iron.
So it's like reverse.
Right, so, yes, it's fission, essentially. Like,
Oh, okay.
Radioactive decay is kind of a type of fission. It's like a specific type where it's not two, like in the most fusion that we think about, it's something like uranium breaking up into two other atoms. In radioactive decay, you have a proton. It's called beta decay. This time, you have a proton that turns into like a neutron and a positron, which is like an anti-electron, and and a neutrino, and or something like that. Yeah, I think that's right. So you when it happens, you get one less proton in the core, right? A proton turns into something else, or it turns into a neutron plus some other stuff.
So
Yeah.
nickel decays to cobalt.
Nickel
but-
decays to
But
cobalt.
it also creates some cobalt, right?
Yeah, so this reaction came it all the way up to radioactive nickel. So cobalt is between iron and nickel. So, but then the cobalt decays to iron. So the nickel decays to cobalt, and the cobalt decays to iron. So what you're left in the end after all this decay is iron. But that decay creates energy, and it happens slowly, and that powers that tail of this supernova. So, where do we get heavier elements? You know, we talked about fusion. In equilibrium fusion, we can fuse all the way up to iron. In non-equilibrium, we can fuse 2 spots up to radioactive nickel. So where does the other elements come from? Where do they come from? So the reason that fusion can be difficult and why we need high heat is if you're trying to put 2 nuclei together, even just 2 protons, but it gets more if you have 2 big groups of protons, 2 nuclei that have a lot of protons in them. If you're trying to push them together, they're going to be repelled away from each other because they're both positive. So, it's just like when if you have 2 positive magnets and you try to push them together, they're going to be pushed away from each other. So these things are pushing away from each other. So you have to get them going fast enough that they can smack into each other. Once they smack into each other, something called the strong force grabs on and holds them together. But the strong force only works on really short distances. If you can't get them close enough for the strong force to grab them, then they're not going to stick together. So you have to get them going fast enough so they can get close enough over this, being repelled. So that's why it's hard to get a proton into a positively charged nucleus. But a neutron doesn't have any, it just has a neutral charge. So a neutron, it's a lot easier to stick an extra neutron in that nucleus. And what a neutron can do is once it gets in that nucleus, it can turn into a proton and an electron. It can break apart and turn into a proton and electron. So it's like, you've got your proton and your electron, your +1 charge and your -1 charge, and they're holding each other so close that their charge cancels out and they're a neutron. It's a little bit more complicated than that. It has to do with quarks and up quarks turning into down quarks and stuff. But, I like to think of it as like a proton and an electron standing on each other's shoulders, and they're wearing a big coat, and they're like, I'm a neutron, and then they get inside the star, and they take their coat off, and they're like, surprise, I'm really a proton and an electron. And then the electron runs out of the atom, and the proton stays, and all of a sudden it's a new element. It's a heavier element. So there's 2 methods of this happening. The S process is the slow addition of neutrons. So you have 1 neutron join in, break apart, jump up 1 spot in the periodic table. 2 neutrons join in, break apart, jump up 2 spots on this periodic table. You kind of slowly jump up spots on the periodic table. This happens in something called asymptotic giant branch stars. It's a phase in the red giant thing. It's in shell burning. You don't really need to know that or what, and you just kind of know it happens. The R process is rapid addition of neutrons. This is when you have a bunch of neutrons really fast entering the nucleus, and then they all break apart, and you jump up a bunch of spots on a periodic table. So in order to have the R process, in order to have rapid addition, you need a lot of neutrons. And there's really only 2 places that we know of that you have a ton of neutrons. That's in a core collapse supernova, that's supernova type 2, when that core is collapsing into a neutron star, you've got a bunch of neutrons hanging around, and they can do this. And the other place is in when you have two neutron stars that merge, you can have this R process. So all of the heavier elements come from these two processes. They're both types of neutron capture. One is just slow and one is fast. One you just jump up 1 or 2 spots at a time. One you can jump up tons of spots at a time on the periodic table. Okay? So, special relativity. This is very complicated and weird. The big things to remember are the speed of light is the same in every frame. It doesn't matter how fast you're moving, you will always measure the speed of light to be the same thing. If you're trying to measure the speed of a car and you're standing by the road, you're going to measure that car going at 100 miles per hour. If you're at another car going the same speed and you look out and say, how fast is that car going? You're going to say it's not moving at all, right? Because you're going at the same speed. Light doesn't work like that. It doesn't matter how fast you're going. You can be going half the speed of light, and light will always measure to be the same speed, the speed of light. So that's something that's really important.
Does that relate to those questions where it's like you're in a spaceship, like you're in space, the speed of light changes?
Right. So like if you're going half the speed of light and you shine a flashlight, then how fast is that light moving? If it worked like other things, then you would measure that light as moving half the speed of light because you're already going half of it, so you're only measuring the other half.
Uh-huh.
But with light, it's different. It doesn't matter how fast you're going, you're always going to measure that
So
light going at the speed of light. Yeah.
Okay.
Light always goes at the speed of light. Some weird things happen the faster that you go. The faster that you go, the slower time moves for you. Your clocks tick slower. So if you are traveling really fast and someone else is standing still, and for you, on your little stopwatch, you time a minute, and then you stop, and you ask them what their stopwatch says, depending on how fast you're going to go, it's going to say longer. If you're going a certain speed, it's going to say it was 5 minutes for them. If you're going faster than that, maybe it'll be 10 minutes for them. Your clock ticks slower. 1 minute for you is like 5 minutes, 10 minutes, 10 years for them. Distances contract in the direction of motion. So if I'm standing still and I measure how long this table is, I get some measurement. If I'm walking along this way very, very fast and I measure how big this table is, I'm going to get a shorter measurement than I did when I was standing still. And then the faster you go, the more your mass increases. So this kind of conspires to mean that nothing can go as fast as the speed of light. Photons go the speed of light, but they don't have any mass. Something with mass, as it speeds up, its mass increases, it weighs more, and it takes more energy to get it going a little bit faster, to the point where it would take an infinite amount of energy to get something going up to the speed of light, because once it gets close, it's so heavy, it would take so much energy to get it going any faster. Okay? General relativity, these are kind of related. This is the idea that mass creates warps in the fabric of space-time. If space-time were like the big elastic sheet, mass would be something kind of weighing it down. Matter and light move in straight lines through curved space-time. So if I walk outside in a straight line for really far, eventually I'm going to walk all the way around the Earth, right? If I just go in a straight line. So I walked in a straight line across a curved Earth. So I walked in a straight line in a circular path. Does that kind of make sense?
Mm-hmm.
So it's a similar thing here. That, I always think, to me, as I'm walking around the Earth, I'm always going in a straight line. But somebody outside the Earth would look and say, I'm going in a circle. So light or matter always says, I'm going in a straight line. But if you pull out and look, it's actually curving. And the closer, the heavier a mass is, the more it warps that space-time, the more it makes things curve around it. And things react to the curve more based on how fast they're going. If you're going really fast, you're not going to be curved as much as if you're going really slow. Something that's going really slow near here, might fall into this. But if it's going really fast, it's going to kind of zip by.
And what's the circle? Is that Earth? Is it?
It's any mass.
Oh, okay.
Any mass does that.
Okay.
So if this were the sun, then the Earth is orbiting around this sun, around here, and the Earth has its own little dip, and the moon is orbiting in that little dip of the Earth.
So it could be like.
Yeah, a bunch of different ones.
Mhm. So light also travels in these curved lines through space. So there's this phenomenon called gravitational lensing, where if you have something with a lot of gravity, light will bend around it. And if that gravity is between us and the thing emitting the light, it's going to look like it's in a different direction, right? So this star emits light, and it bends around the sun to us. But we think, okay, light travels in a straight line, so this star must be over here.
And why does it bend around the sun again?
Because the sun creates this dip,
Oh.
and the light bends around the dip.
Just kind of like the Earth's orbit.
Mm-hmm. But instead of orbiting around, it just curves. Just like for special relativity, when you go really fast,
Does that have to do with the fact that that is traveling at the speed of light, and therefore it doesn't get caught in that orbit?
right. And so that's when we come to black holes. Like black holes, it will get caught in the orbit
If it's
because they have more gravity.
Sizable.
Right. If it's close enough in. Mm-hmm. So just like I said in special relativity, the faster you go, the slower time moves for you. In general relativity, the closer you are to like a big gravity source, the slower time will move for you. So this was like, if you've all seen Interstellar, Matthew McConaughey goes to that black hole and comes back out, and he's like the same age he was, and his daughter back on Earth is an old lady. Because time moved more slowly for him as he was near the black hole, and it moved faster for people back on Earth.
Because of the speed he was going.
Because he was closer to a gravity. So it's the same effect from two different sources. Either you can go really fast, or you can be really near something with a lot of gravity. And the closer you are to that pull of gravity, the slower time will move for you. So as you get to something, like as you have it closer to an infinite pull of gravity, or as you get closer to the speed of light, time's going to slow to a stop, but it's never going to reverse. It's only going to get to a stop, because you can't go faster than the speed of light, and you can't get more than infinite gravity. Right? So that's kind of the end of it.
Because black holes have infinite gravity?
Essentially, gravity,
Because they just subject within
the equation for gravity is proportional to mass over radius squared. So as this radius gets smaller and smaller and smaller and smaller, as this goes down to 0, this goes up to infinity. Right? So this is how far away you are from it. And a black hole is just a single point. So as you get closer and closer and closer and closer to the black hole, to that single point, the force of gravity is going to go up and up and up and up.
So is this relationship also why, if you're outside of the whatever that thing is called?
The Schwarzschild radius or the event horizon?
Yeah.
I think this is
A black
this is
hole
little
functions
gravitational
similar
pull.
to its mass,
Right.
but once you're inside it, then it's the radius that starts to
Well,
matter.
so the radius always matters. The mass is going to stay the same, but if you're out, so it basically always, the laws of gravity stay the same, no matter what. So if you don't change your mass and don't change how far away you are from the center of mass, then the gravity that you feel is going to be the same. So if I collapse the sun down into a black hole without changing its mass, I'm not changing how far away I am from the center of it. The gravity that we're going to feel is the same. But if you get closer in, then the gravity goes up. And if you get closer in past the event horizon, then the gravity is so strong that light can't escape. Okay?
Miranda?
Yeah.
Are you gonna stop right at 12?
I don't know if someone has this room after this. I can keep going. I didn't. This takes. There's so much. But if someone needs this room, we'll have to stop. But I can keep going if not. So escape velocity is this idea that there is a minimum speed that you have to go to like not fall back down to an object. So if we are on the Earth and I throw something up slowly, it's going to fall back down. If I throw it up really fast, like if I attach a rocket engine to it and throw it up really fast, then it's not going to fall back down. So there's a limit somewhere in between those two speeds where it's not going to fall back down, and that's your escape velocity. This is the formula for it. It depends on the mass of the object you're escaping from. So the planet you're trying to get off, the star you're trying to get away from, the black hole. It depends on how far you are from the center. It does not depend on how massive you are, like what your mass is of the object trying to escape. So the escape velocity from the Earth is the same for something really light versus something really heavy.
And R is radius?
R is radius. It's radius from distance you are from the center of whatever is creating whatever mass is creating the gravity. So on the Earth, if you want to know the escape velocity from the surface of the Earth, that R is going to be the radius of the Earth. It's the distance from the center of the Earth. Huh? G is just a constant. It's just a number.
Thank you.
Okay, so black holes, like I said before, when that massive star has that type 2 supernova, it makes that neutron star. Sometimes material can fall back onto the neutron star. It gets so big that the neutron degeneracy pressure can't hold it up anymore, and it's going to collapse all the way down. There's nothing to stop the collapse. It's just going to collapse down and down and down and down and down and down until it essentially has 0 radius. So it's just like a single point. Did you have a question?
If we have to go early, can we collect our quiz for?
Yeah. You can also have merging neutron stars that make black holes. So from that escape velocity formula,
Would not merging neutron stars always make a black hole?
I assume so. I don't know. They're just not the only way that a black hole can be made.
Yeah.
But yeah. So in this formula, there's some radius at which our escape velocity is the speed of light. And that radius is called the Schwarzschild radius. If you are inside that radius, even light cannot get away from the gravity of it. And light is trapped inside of it. Yours is going to be in that stock because I didn't bring it up. Okay. If you take that radius and you make a sphere out of it, that's called the event horizon. It's not a physical barrier. It's just the distance at which light can escape. So if you're outside of this event horizon, light can be bent around it but get away. Light that is created outside of it can get away. If you're inside this event horizon, nothing can get away. The gravitational influence is still pulling outside the event horizon, but light can escape. As your mass increases, your event horizon gets bigger. And then this kind of I talked about how if the sun were replaced by a black hole of the same mass, and we stayed at the same spot, then we wouldn't even notice, except for there's no more light in the sky. So we would notice, but not. So we detect these stellar mass black holes. We see something emitting X-rays. We look at it with the telescope. we see a star moving as if it were in a binary system. So it's rotating with something, but we can't see what it's rotating with. If it were, we know from its movement, we can measure the mass of what this other object is. So we know that it's, maybe 5 solar masses. We know it can't be a white dwarf because white dwarfs can't be 5 solar masses. We know it can't be a normal star because if we looked, then we would see a normal star. So it has to be a black hole. And these X-rays come from, as this black hole, it can kind of suck in gas from the star. The gas spirals around the black hole. It heats up, and it emits X-rays. And then the Milky Way, this is our galaxy. It is a barred spiral galaxy. This is like a top-down view and a side view. There's approximately 3 times 10 to the 11 stars, plus gas, dust, asteroids, planets, and something else. In the middle, there's a bulge. This contains old stars. There's the disk. This part, that's the bulge. There's the disk. It has gas, dust, and young stars. This is where all the dust and gas is, so this is where new stars are formed. The stellar halo is like a big sphere around everything that has old stars, globular clusters, which are these groups of stars, the remains of accreted dwarf galaxies, and this is like low density. It's like almost 70% of the stars are in the disk, about 30 are in the bulge, and then just a few left are in the halo. And then in the center of the galaxy is a supermassive black hole. It's about 10 to the 6 solar masses. We know it's there because first it was detected as a radio source, and then they looked there and they watched stars orbit around something there. And so they were able to measure from the orbits of the stars how big it was.
Could a star get pulled in?
They're not close enough to get pulled in. I mean, like, technically yes, but, like, they are far enough that they're in a stable orbit.
Until we get smashed by it.
Until something happens, yeah. And then there's the dark matter halo. When we measured the rotation curve of the galaxy, which compares distance from the center to rotation speed, we saw that the stars on the outside of the galaxy were moving a lot faster than we thought they should, than they would if the galaxy were just made up of gas and stars and dust. So we learned from that flat curve that there's a lot more mass in the galaxy than we can see. We didn't know what that mass was, so we just call it dark matter. And it's like 90% of the mass in our galaxy is dark matter. So it's everywhere. Like when you look up at the night sky and you see all those stars, you look at the Milky Way and you see that big pretty thing. Like all of this that we can see, that's only 10% of what's actually in our galaxy. And the rest is invisible to us. In the 1920s, there was this great debate. We started being able to see other galaxies, and they wanted to know, are these like part of the Milky Way, or are they their own separate galaxies? And they are separate. They come in lots of different shapes and sizes. Some are a lot bigger than the Milky Way. Some of them are smaller. The Milky Way is part of a cluster, like our group is called the local group. It's made up of the Milky Way, Andromeda Galaxy, Triangulum Galaxy, and a couple hundred dwarf galaxies. You don't need to know like specific ones. I mean, it's good to know Andromeda is one of them. Just know it's like maybe 200 galaxies in total. And the Milky Way is one of the biggest in the local group, but it's not one of the biggest overall galaxies. And then we started seeing these weird things called quasi-stellar objects, or quasars, and or AGNs, active galactic nuclei. What this is, it is in some galaxies, there's a supermassive black hole that is emitting radio waves, and matter is falling into these black holes, and it's heating up, and you get these giant jets that come out of either end.
Jets of what?
Jets of matter.
Oh, okay.
Mhm. Yeah. So our black hole is pretty dormant. It's not really doing much, but some black holes are sucking things in. That stuff gets heated up. Some of that stuff gets pushed out
from the black hole?
So it's not from the actual black hole. It's from the disk around the black hole. So stuff is
Like
falling in here, then the black hole here, and then kind of around the black hole, you have stuff getting pushed out. So it's not too close to the black hole, or else it would
Get sucked in.
suck in. But it's moving fast enough that it can escape out
What
here.
is what's pushing it out of the orbit? If you can call it that, not the orbit, I guess, but the circle.
So it's we don't super know that well. It has to do with like really strong magnetic fields in this like spiraling accretion disk.
Mhm.
The magnetic fields build up really strong, and they can kind of send stuff out that way.
Okay, thank you. What does AGN stand for, sorry?
Active galactic nuclei.
Right, thank you.
Expansion of the universe. So this idea, we can measure how fast things are moving away or towards us from something called the Doppler shift. And this is this idea that the measurement of a wavelength changes based on how fast the source is moving towards or away from us, or if we're moving towards or away it. So if the source and the observer are moving towards each other, the measured wavelength is going to be shorter than what it was emitted at. And that's called blue shift, right? If you get a shorter wavelength, you're towards the blue end of the spectrum. If they're moving away from each other, the wavelength gets measured as longer. This is a red shift. So we know what the pattern from a star or a galaxy should look like. We know what their emission line pattern should look like. If we measure their spectrum and we get something that looks like the pattern that we know, it's just been shifted, then we know how fast, by how much it's been shifted, we know how fast it's moving away or towards us and what direction. If it's been shifted towards the red side, then we know it's moving away from us. If it's been shifted towards the blue side, it's moving towards us. So we were able to compare the distances to galaxies to how fast they're moving towards or away from us. And they found that almost all the galaxies are moving away from us. And the farther away from us they are, the faster they're moving away. And the best explanation for this is that space-time is expanding uniformly. So it's an increase in distance between 2 points as space-time stretches. So if space-time is like an elastic, then it's stretching out. So if you have like 2 points on that elastic and it's stretching, they're not moving across that elastic, but they're getting farther away from each other as I stretch the elastic between them. So expansion is just a stretching. And light travels through space-time, and as that space-time stretches, the light stretches out too. So that redshifting, that stretching out of that wavelength, it works like a Doppler shift. And we can measure the expansion from that, how much the light has been stretched out. So that is the end of quiz 3.
Can I make a quick announcement before we move on? So I don't know if everybody's seen, but our TAs are putting in a strike for themselves, which has a lot to do with the fact that their wages are way too low for the cost of rent in Santa Cruz. And so one of the asks is that on your final paper, you just write a quick note to the professor that you support the grade strike. Essentially what they're doing is refusing to turn in grades until the university meets their demands, which ultimately won't affect us because we're going to get our grades at some time, and also, allows them to get a living wage. So I just think this is a good example of like how hard our TAs work for relatively nothing. She's putting in so much extra labor just so we do well. Like so much of this is actually like not even expected. So just to say, like if you feel like it, I think the least we could do is write that note and make sure that the university knows that we support fair wages for the type of work that our teaching assistants do.
Thank you for saying that. On a note about the strike, some graduate students make as little as, take home as little as like $18,000 a year to live on in Santa Cruz. Like that's nothing. I personally pay more than 50% of my wage in rent, and I'm lucky. our department is, they fund us better than some. They fund us during the summer. Some graduate students don't get paid at all during the summer. I can get funded through my professors, like through my advisor during the summer, so I'm lucky. I'm also lucky in that I have a supportive family. I know if worst comes to worst and I can't pay my rent, I'm not going to go homeless. I'm not going to go hungry. Like, my family's there for me. So this low wage really disproportionately impacts less privileged students, students of color, students with disabilities. A big one that it impacts is first generation students. A lot of first generation students, they're not supported by their families, they're supporting their families. They're trying to save up money to give back to their families. So paying such a low wage really limits access to higher education for less privileged people, and it turns higher education into something that's only like elite people can access, and that's not right. Like, everybody should be able to learn, everybody should be able to come and contribute to research, people's voices should be heard. We shouldn't limit it just to those who were already lucky enough to have extra sources of income or supportive families. Not all grad students, like, I'm lucky enough I don't have to have a side job. I can put a lot more time into this. Some people take longer to finish their degree because they have to work 2 jobs on the side just to pay rent. And then, it takes longer for them to finish, so they spend longer earning a low wage. And it's rough. I don't want to do anything that's going to negatively impact you guys. If anybody has like an urgent need for a grade, if you're on academic probation or something and you need to know that you passed the class to get off it, if you're graduating, if you have some sort of application due that really needs your final grade, come to us. We'll work with you. Like, we don't want anybody to be negatively impacted, but I do think it is really important. Like, yes, the cost of living adjustment would be really useful to me, but it's not, my participation in this is more for the people that, if they don't get this, they can't stay grad students. They have to drop out, or they go homeless, or they don't eat. And I don't think it's right for us to treat our labor at this university in that way. So I hope that you guys aren't negatively impacted by this. I know it can be. We're still going to do your tests. We're still going to grade them. We're just going to wait to submit until there's some movement on this. Yeah.
So is the no review on top, is that like a sort of consent of the drama grades, or are they going to be withdrawn regardless? Like, I want to support it, but I was just wondering what
That's what the strike is saying that they're
Yeah.
not going to do it without the university moving on that. So the note on the top is just working to kind of lessen the pushback that our TAs will likely get from their departments, and it's essentially saying like, no, fuck that, we support it. Okay.
Yeah, so again, like, if not having a grade is really going to negatively impact you, let us know. We're going to work with you to make sure that you're not harmed by this strike. This is not about punishing students. A lot of professors have signed on to this, and Dr. Bolte said that I haven't really talked with Dr. Bolte and Dave exactly about what we're going to do, but they both said that they will, like Dr. Bolte said, that he's going to support what we decide. And I think that's really important to stand up for not just all grad students, but especially less privileged grad students who would be pushed out of their programs or go homeless or go hungry if something like this doesn't pass. So.
Thank you.
And an extra note, if you are graduating, the strike shouldn't affect the delivery of your diploma.
Yeah,
So
I
that shouldn't
have
be a
like a little, so like even academic probation like shouldn't matter. Like, an incomplete will never lower your GPA or anything. But if you are concerned about something like that, just come to us. Like, we're here to help you, and we want to make sure that everybody gets what they need to get. Okay, so that's the strike stuff. I think technically we're out of time. I can go over quiz 3 if you guys want me to.
And then don't you have a review on quiz 4 online?
I do. Or I have, so, Yeah, I can put the PowerPoint online. So I'm gonna go over quiz 3, and then if it's okay, I might just go over the problems from quiz 4 instead of going over the review slides because I gave them these a couple days ago. Did you have a question? No. Oh, that's
Do you want
Yeah.
to oh yeah, totally. Thank you.
Yeah, it's gonna be just like this except longer.
Oh, they're alphabetized. That's nice.
Yeah, mine are alphabetized. I don't know what these are.
No, they're not. Of course not.
Okay, so for quiz 3, this says which of the following are predictions of special or general relativity? The first one says if you're in a spaceship moving at 0.9 the speed of light and shine a flashlight in the direction of travel, you'll measure the speed of light beam to be 0.1 c. And that is false. The speed of light is always going to be measured at c, the speed of light.
What is the,
Do you have extra quiz 3 just so I can look at it?
I don't think I do.
Okay, I can look online.
They're online for sure.
Sorry.
No problem. So mass warps the space-time fabric of the universe. That's true. Time reverses as an object approaches the speed of light. That's false. Time's going to slow down to a stop, but it will never reverse. And then electromagnetic radiation traveling near mass will appear to bend as it follows a straight line through curved space. And that's true. So then, which of the following best describes the calculation of the Schwarzschild radius for an object with mass m?
Should be the last one.
So the Schwarzschild radius is the radius at which the escape velocity is the speed of light. So you plug in c, the speed of light for your escape velocity. Radius you replace with your Schwarzschild radius, and then you just manipulate that equation to solve for your Schwarzschild radius. So that's going to be that first one on there. 4 says, which of the following are true and which are false in describing an event horizon? So it is the distance from a singularity where the escape velocity is the speed of light. That's true. That's like the definition of it. It is the extent of a gravitational influence of a black hole. That is not true. There's still a gravity pull outside the event horizon, but it's not enough that light can't escape. Light can still escape from outside the event horizon.
This one, the last
The event horizon of a 1,000,000 solar mass black hole would be much smaller than that of a 10 solar mass black hole. So that is false. If you get more mass, your event horizon gets bigger. So the equation for event horizon, or for the Schwarzschild radius, is Q over U squared. Yeah, of course. Yeah. So as your mass goes up, your radius goes up. And then no electromagnetic radiation can travel from inside the event horizon to outside. That's true. If you're inside the event horizon, your escape velocity is faster than the speed of light, so light can't escape and travel outside. 5 says, which of the following are processes that produce elements with atomic number larger than iron? So the addition of neutrons to existing nuclei, followed by beta decay. That's when a neutron goes into the nucleus, splits into the proton and the electron. The electron gets emitted, the proton stays in there, and it moves up. So that's true. The fusion of helium to light nuclei resulting in the even-odd effect. So heavier than iron, not going to be normal fusion. So that's not true. Non-equilibrium fusion reactions during a supernova explosion, producing cobalt and nickel, that is true. That's that supernova type 1. You get those non-equilibrium ones, making cobalt and nickel. And then the rapid addition of protons to existing nuclei, that is not true. It's hard to get, you can't get a bunch of protons in, one after another. What is the evidence for a dominant dark matter component of the galaxy? So this is that rotation curve. I have a picture of it in one of those slides. Right. Yeah, so this this right here is the rotation curve of spiral galaxies, and it's flat. We expect it to go down. We expect stars going out here at a large distance to be going slower, they're actually going just as fast as stars on the inside. So that tells us there has to be a lot more mass inside the galaxy, and that's that dark matter. So for this, it's the rotation curve of the galaxy is flat. Stars in the outer parts of the galactic disk orbit faster than expected, based on stars and gas seen inside their orbits. 7 says, which of the following provide evidence for space-time expansion? So we know things are expanding because almost all the galaxies are moving away from us. I have a, let me see. Where did my... Oh, no problem. I had a little simulation. Alright. My computer's like, stop doing so many things on me. So, if all of these coins on this balloon are galaxies, and then you inflate the balloon, then all of the galaxies move away from each other. They don't move on the balloon. They stay in the same spot as the balloon. But as that balloon expands, all of the galaxies, like if you're looking at this galaxy, everything's moving away from it. If you look at this galaxy, everything's moving away from it. So no matter which one you pick, everything's moving away from it. So either we think, okay, our galaxy is super special and at the center and everything's moving away from it, or it's uniformly expanding and no matter which galaxy we were in, we would see everything moving away.
Be like when you used to think that everything's revolving around the
Right. That doesn't make any sense. We're not that special. That's kind of one of the kind of two things about like Einstein had these two kind of ideas, and that are that the universe basically looks the same in any direction. Like no matter which way you look, it basically looks the same, and no matter where you are in it, it looks the same. Like we're not in a special spot. So that's that deflection of. So this is space-time expansion. Deflection of starlight seen during a solar eclipse. That is gravitational lensing. So that's general relativity, not space-time expansion. Energetic jets observed near QSOs and active galactic nuclei. That doesn't really have anything to do with expansion. And then blue shift of light from the Andromeda galaxy. So the Andromeda, so I said most galaxies are moving away from us. Andromeda is one of the few that is moving towards us. So it's blue shifted. Expansion pulls everything apart. Gravity pulls things together. Andromeda is close enough that its pull from gravity is stronger than the pull from expansion. So it's moving faster, it's moving towards us from gravity, away from us from expansion, but it's moving faster towards us than it is away from us. So overall it's moving towards us. But things that are farther away from us are moving faster away, so their expansion velocity is bigger than their gravity pull. So you have to be really close for gravity to win. So Andromeda is moving towards us, but most of them are moving away. So that is not evidence for space-time expansion because that's one of the few that's moving towards us. Which of the following are part of the scenario for supernova 1? So mass transfer from a close companion onto a white dwarf. That's where it starts. The collapse of a white dwarf whose mass exceeds 8 solar masses. So that is not true. It is the collapse of a white dwarf, but a white dwarf can never be 8 solar masses. 1.4 solar masses is the limit for a white dwarf. The formation of a neutron star, that is supernova type 2. And then fusion reactions in a collapsing white dwarf that produce elements including radioactive cobalt and nickel, that's true. Which of the following are part of the reasoning chain that leads us to believe that binary system Cygnus X1 contains a stellar mass black hole?
So I think this is one that a lot of people got wrong.
The binary one?
Yeah, mainly because it talks specifically, it was kind of tricky because it talks about a very specific binary star system, And if you're thinking about the logic of a black hole,
Mm-hmm.
then you're thinking about 3 solar mass, but this is in reference to 5
Right.
solar
So
mass.
yeah. So X1, Cygnus X1 was one that we talked about specifically in class.
Yeah.
So I think it's one, but yeah, I can kind of see what you mean when you're like, oh, well, it only has to be 3 solar masses. But yeah, so Cygnus X1 specifically is at least 5 solar masses. So the first one says there's an unseen companion in the system that is emitting degenerate electrons. There is something, an unseen companion. It's emitting something, but what it's emitting are X-rays, not degenerate electrons. There's an unseen companion that it's at least 5 solar masses, but is not visible at optical wavelengths, and therefore is not a red giant or a main sequence star. That's true. If it were a red giant or a main sequence star, we would see it. It would be giving off light. There's an unseen companion that is at least 5 solar masses, which excludes the possibility that it could be a white dwarf or a neutron star.
So that would have to be.
It has to be, yeah, it couldn't be, it has to be more than 1.4 solar masses, or more than 3 for a neutron star, so it can't be those. Like, a white dwarf or a neutron star could be dim enough that we wouldn't be able to see it with the telescope, but we know it's heavier than those are. And then the system emits hard, short wavelength X-rays from material heated to high temperature near the black hole. That is also true. And then, which of the following statements about the Milky Way galaxy are true and which are false? So it is a member of the local group of a few hundred galaxies, and that's true. It is one of the largest in mass and radius galaxies we know of in the universe. That is false. It is one of the largest in the local group, but not in the universe. Star formation is still going on in the Milky Way. That's true. In the disk, you have gas and dust forming into stars. And then it is known to contain about 10 to the 5, which is 100,000 stars in total, and a slightly larger number of planets. That is not true. It has over twice that many stars, or over like that number squared as many stars. It has like 10 to the 11 stars and a little bit more planets, because every star has an average of 1.6 planets. So you have more planets than stars. Okay, so I'm going to go over the answers to quiz 4, yeah? Okay, so dark matter has been invoked to explain observations on very different spatial scales. Which of the following indicate the need for dark matter? So, inhomogeneities in the cosmic microwave background at the 10 to the negative 5 level.
No.
So that's those tiny little temperature fluctuations, and those don't have anything to do with dark matter. The flat rotation curves of the Milky Way galaxy and other galaxies, that is dark matter. That is, where's my PowerPoint? That's these flat rotation curves. The formation of large-scale structure in the universe, that is like this cosmic web, and our simulations show that this wouldn't have formed if we didn't have dark matter.
I'm sorry, can you repeat that last thing that we have formed if we didn't have that matter?
This large-scale structure, these like nodes and
The way our galaxy.
yeah. So this is
Our,
the way
universe.
galaxies
Universe.
are. Like if you zoom way out.
Okay.
So these like each dot here is like a cluster of
And are those
galaxies.
black things just dark matter, or?
So those black things are just voids. There's nothing
Oh,
there.
okay.
So the dark matter is clustered with the galaxies. We just can't see it.
Thank you.
Yeah. So these are like galaxy clusters. This is if you zoom way out, and each of these like dots are like maybe a cluster of galaxies.
Because if the voids had dark matter in, then they would have gravitational pull, and they would pull things.
Mm-hmm.
I see.
So where's my other little? I had a little video.
Synapses finding
Oh man, I lost it. Yeah. So like this structure gets more webby over time. Like it started out with everything kind of more evenly spread out, and then things started to clump together.
Okay.
I bet I can find it. And then the clumps kind of got bigger, and as the clumps got bigger, they had more gravitational pull, and so they were able to pull stuff even farther. I had a good little picture. Let's see if I can find it. I must have exited the I think this has the, oh my god, this is moving so slowly. Okay, so while this is loading, so the last one is the acceleration of the expansion of the universe. So that has nothing to do with dark matter, that has dark energy. Okay, here we go. So this is like this is very early on, everything is very much spread out, and then things start to kind of clump together.
And the white is the condensed.
White, like the brighter it is, the more galaxies there are.
Okay. So we can almost think about that as similar to what the
Right.
cosmic microwave
Right, so there's just tiny little parts of that that are more dense or less dense.
Okay.
And then as time goes on, those densities, like that grows. You go from those tiny little fluctuations all the way down to something like this. Yeah. So it goes like here to here to here to here to here to here. So as there's a movie. As time goes on, it gets clumpier and clumpier. I don't know if that's going to load or not. So based on our current data and models, what is the, oh, there we go. Space is cool, right? Like, Z is redshift. So we use that as, so redshift is both a measurement of distance and of time. So and expansion. So a higher Z is farther away and farther back in time. So Z of 0 is right now, and then Z of all the way back is all the way back to like the cosmic microwave background.
Did we study redshift as a measurement of time and distance?
We did do it as a measurement of distance.
Okay.
On the there was a, I don't know if I have it on here. There's a formula for redshift where you take your observed wavelength and your emitted wavelength over your observed, you get redshift, and then there's some formulas that say velocity is the speed of light times your redshift, and then it's also equal to 1 over the Hubble constant times your distance, I believe. So you can get your distance from the redshift, and then if you know distance, then you know how far back it was, because it's however long it took light to go that distance.
Okay.
Right, and then the Hubble constant is the essentially the age of the universe. So if you go all the way back to the beginning, then this kind of cancels off. So, okay, based on our current data and models, what is the most likely long-term fate of the universe? So, the universe is going to keep expanding. So we get more clumpiness like this, but things are going to keep getting pulled apart, and eventually this expansion is going to win out over gravity. Everything's going to get pulled apart.
Why are they expanding? Because they're getting hotter? No, they're going down. So why are they expanding?
So we don't really know. That's this idea of dark energy. Something is making the universe expand.
Okay.
And it's getting faster.
Okay.
So expansion is growing. Right now, at some scales, gravity is stronger than expansion. As expansion gets stronger, it's going to win out over gravity. It's going to pull everything apart.
It's going to cool down until like fusion or something.
Yeah, things are going to cool down. The stars aren't going to form anymore because like all the gas is going to get used up to form stars. The stars that we have are going to burn out. It's going to be dark and cool. So this is the increased expansion rate. Decreased star formation to 0, cooler and darker. Somebody had a Zoom comment. I just want to see these. 4 says the theory of cosmic inflation was originally motivated to understand why magnetic monopoles were so rare in the universe. What other cosmological puzzles does inflation resolve? So the first one says the horizon problem that prevents us from seeing past the nearest supercluster of galaxies. So it solves something called the horizon problem, but that's not what the horizon problem is. The horizon problem is why does one side of the cosmic microwave background and the other side, why are they at the same temperature even though they should never have been close enough to get to the same temperature? And inflation solves that by saying, well, before inflation they were close enough, and then they got really far really fast, and now they're just slowly moving away from each other. The dark energy problem that creates acceleration expansion. Where is the dark energy problem? Expansion is accelerating. We don't really know why, but inflation doesn't tell us why. The origin of fluctuations that became the seeds of galaxies and structure formation is quantum fluctuations that grew via inflation. That is true. That is those tiny little, what started off, those tiny little things that grew into that. And then inflation allows us to understand what existed before the Big Bang. That's not true. It doesn't tell us anything what happened except what happened just a teensy tiny bit after the Big Bang started. So I skipped 3. I'm going back to that. Is which of the following describe the large-scale distribution of matter in the universe? So dark matter is uniform in all directions. Visible matter is highly clumped. So we know visible matter is highly clumped, but so is dark matter. So this is dark and visible matter is highly non-uniform with clusters, filaments, and voids. That's true. That's the structure that we see. Matter is uniformly distributed except for small density variations at the level of 10 to the negative 5. When we say small density variations at the level of 10 to the negative 5, we're talking about the cosmic microwave background, not the large-scale structure.
How come y'all just don't put CMB? Like, how come you just don't put cosmic microwave background?
I mean, I put CMB sometimes.
Yeah. Because of the number? Is that Because I thought I was just didn't know the value, but of the 10 to the negative 5. Never mind.
Yeah.
Right, but so matter is not uniformly distributed except for this. What is uniformly distributed, is the cosmic microwave background.
Right. And
That's what I'm saying.
And the cosmic microwave background is like that. I'll go over that actually. Never mind. This is not the cosmic microwave background,
No.
right? This is the
This is
structure.
not.
of-
Right, so this kind of beginning, this is kind of what caused the cosmic microwave background. This is what, when we see the cosmic microwave background, this is kind of what we're seeing, right? We can't see through that.
Right, because it was like the primordial fog or whatever.
Yeah, exactly.
Okay.
And so that primordial fog, the light from that has been stretched out as it came to us, and it looks cooler than it actually was. But what we're seeing is when the universe looked like this.
Okay.
And then quantum fluctuations before inflation produce galaxies that are moving away at the speed that is proportional to their distance. That is a true statement, but it doesn't describe the large-scale structure. The large-scale structure is specifically this filaments and voids and nodes. So 5 says, which of the following are true and which false regarding the cosmic microwave background? It is radiation that originated about 380,000 years after the Big Bang. That's
Are you
true.
on 4? Sorry.
Yeah, I'm on 5.
Oh, I see.
I skipped 4, and I skipped 3, and then went back to it, and I'm down to 5.
Right.
So it is seen as microwave radiation in every direction of the sky. That is true. Everywhere we look, every direction, behind all the galaxies, we see the remnants of that fog, the light that came from that fog.
Can it be considered interspersed?
I mean, the light is interspersed in that, we are getting it now as at the same time that we're getting light from other stuff, but the light comes from behind the galaxies. So we see,
it's more of a wall.
right, we see the galaxies in front of it.
Okay. Because that's what's doing
Everywhere in a whole sphere,
Mhm.
everywhere.
Yeah, every direction we look, we see it. Because anywhere we look, we're looking back in time.
Yeah.
And so anywhere we look, we can look all the way back to the point the universe was foggy. And that's what we see when we see the cosmic microwave background.
Okay, thank you.
It is the relic radiation from the first stars that formed after the Big Bang, redshifted by a factor of 100,000. So it is relic radiation. It is redshifted by a factor of 100,000, but it's not from the first stars that formed. It's from this when the universe was foggy. and it has the spectrum of a 3000 Kelvin ionized plasma, redshifted to appear like a 2.75 Kelvin plasma. That is true. Sometimes we say 3, sometimes we say 2.75. I'm sorry that is confusing, that we have not been consistent on that. In the lectures he said 3, and then on this he said 2.75. I think I went back and forth in my section. It's just rounding.
Okay.
If we say 3 or we say 2.75, it's just rounding. It's the same. Right, so there was this 3000 Kelvin ionized plasma. The light stretched out as it got to us. And by the time it got to us, when we plug it back into that formula for temperature, we get out 2.75 Kelvin. All right. Which of the following are true and which are false? So the total star formation rate in the universe has been relatively steady since about 1 billion years after the Big Bang. That is not true. About 1 to 3 billion years after the Big Bang, star formation rate peaked, mergers peaked, and quasars peaked. So at that time, the universe was closer together. The galaxies were closer together because the universe was smaller. So the galaxies, it was easier for them to merge. When galaxies merge, you get quasars and star formation. So all of them peaked at the same time.
I'm sorry, at 1.2 million years, you said?
Like between 1 billion to 3 billion years.
I see.
Quasars are more common now than at any time in cosmic history. That's false. They were more common in that peak period.
So star formation, quasars, and what else?
Mergers,
Thank you.
galaxy mergers. And the star formation in the quasars peaked because there was more galaxy mergers.
Okay. Thank you.
The merger rate of galaxies has been steadily decreasing over time as the universe expands. That's true, right? Galaxies, as they are getting farther away from each other as the universe expands, they're not going to merge as often because they're getting farther away. And then dark matter is much more common than the type of matter that makes up stars, planets, and humans. That is true. Dark matter there's a lot more dark matter than normal matter. 7 says, which of the following are fundamental particles? The proton is not. It is made up of quarks. The electron is a fundamental particle. The hydrogen atom is made up of protons and neutrons and electrons. So that's not. And the up quark is a fundamental particle. Which of the following provides supporting evidence for the hot Big Bang model? Abundances of elements formed by the R process match hot Big Bang predictions. So R process, that's that rapid addition of neutrons, that happens in supernova type 2 and merging neutron stars, not in the hot Big Bang. So that doesn't tell us anything about the hot Big Bang. The merging neutron stars. The predicted abundances for helium-4, helium-3, hydrogen-2, and lithium-7 at the time of element freeze-out, around 300 seconds after the Big Bang, match observations. That is true. 300 seconds after the Big Bang, the universe cooled down. There wasn't any more fusion that could happen. So whatever was made when it was cool enough, there was no more fusion. That's just how much we had. We know how much we should have had. We can measure how much we did have, and it matches up. The presence of a ubiquitous background radiation, characteristic of that from a 3K solid, that's that cosmic microwave background radiation. That's part of our evidence. And the requirement of dark matter to explain the development of large-scale structure, that is true, but it doesn't have to do with the Big Bang. That has to do with stuff later on. Which of the following techniques are used to detect planets orbiting stars other than the sun? Measuring small periodic radial velocity variations in the exoplanet host stars. That's that radial velocity method. Measuring a small reduction in brightness when a planet passes in front of a parent star. That's the transit method. So those two are true. Using parallax measurements of the nearest planets outside the solar system. So in order to use parallax, we have to be able to directly see this thing. And we cannot directly see these planets. We measure them normally by how they affect their star. Unless we're doing direct imaging, but that is, that's not nearest planets outside our solar system, and that has something to do with parallax. Using the largest radio telescopes to beam radar signals to all the stars in the solar neighborhood, to identify objects too faint to be seen with optical telescopes. No, we haven't talked anything about doing something like that. So that's just not something that we do. And then the last one says, which of the following are true and which are false regarding what we know about exoplanets as of 2019? So the majority of stars have at least 10 exoplanets in orbit. That is false. The average is 1.6. We've only found one other that has 8, like ours does. 5 or 6 is a pretty common amount, but definitely not at least 10. The most common type of exoplanet discovered to date is approximately the mass of Jupiter. So this is false. It's approximately the mass. It's between the mass of Earth and Neptune, but we gave you this point no matter what you put, because we weren't consistent. It used to be Jupiter until the Kepler missions. Some of the plots on the slides were kind of confusing, so I wasn't clear. I told you wrong information, and I wanted to make sure nobody got points taken off for that, so I made sure that we kind of threw that question out and just gave you a point no matter what. So it doesn't matter if you put true or false, but it is false. Earth to Neptune size is the most common. Most exoplanets discovered to date are very close to or in the habitable zone of their host stars. That is false. They're normally like inside of the habitable zone. So you have, because they're very, very close to their star. You have a star. You have the habitable zone, which is just this ring here. And then most of the exoplanets we find are like inside here, really close in. And then based on observations to date, it is estimated that there are more planets in the galaxy than there are stars in the galaxy. So I said that there's on average 1.6 planets per star. So there's going to be more planets than stars. So that is true. And that is all the questions on quiz 4. Sorry, this ran so over again. But
Thank you so much, Miranda.
I have a video. Alright, I'm glad this was helpful. I'm going to turn this video off.